is only regression. So the Excel sheet has both the regression as well as classification. So
Yes.
the question I'm having is, what are we supposed to do? Because I see two problem statements here.
So go down, further down. There is no, okay, there is no,
and there is no proper input, because you see there are two contradictory statements. Here the problem statement says regression and classification. Same problem statement here repeats only regression. And the data set has both regression and classification. Like if you see the Excel sheet here, trip demand, this is a regression part and this is a classification. Fine enough. But what are we supposed to do?
show me that document again. Okay. Come down, data processing. Scroll down, please. Regression models, sites. Okay, if you see the steps, in the steps, there is no discussion about classification.
Yes.
Okay, so you can remove the first problem statement.
Okay.
Stick only to regression.
Sure.
Okay. Okay. Yeah.
Sure. So we'll ignore this particular column. We'll just go ahead with this data set. Sure.
Yes. Yes.
Yeah.
If that column has to be ignored, if the column maybe that column is part of the independent variables. I do not know. So
sure.
If check whether that is that's a column that needs to be ignored.
So sure. That column technically indicates that if the trip demand is exceeding a threshold or not. So if it is exceeding 22, then it goes to 1. Otherwise, it's 0. So if we consider P class as a a dependent variable, then there will be a leakage of.
It's a there is a direct correlation between both of them. So we need to discard this.
Then it has no extra meaning.
Yes.
See, that's the thing. See, the column is there, and if you have figured out that this column has no additional value than the trip demand itself, then you write that as one of your observations and say you are dropping out this column.
Sure.
Okay. Yeah.
Hello. Hello. Good evening. I want to ask about. I can see there's a template of the assignment. Shall we have to follow all the parts based on the template, or we can just write all the content by ourselves, but not follow the template?
See, I would like you to follow your own way of presenting. There is nothing wrong in that, except that ensure that whatever has been asked for, you address all those questions.
Okay, I have all the content inside, but just the arrangement of the content is different.
Yeah, that's okay. That's okay.
Okay, thank you very much.
Yeah. Okay. We will move on to today's session. Check. Yeah. So I think this is where we stopped last time. So I'll give a quick recap of what we did. I'm not going to go through the entire thing. It's going to be a quick recap. So we started with the problem of predicting the value for one variable based upon the values of another variable. So we have one dependent variable and one independent variable. Both of these are continuous numbers. Therefore, this problem, we call it as a prediction problem. Generally, we use the term regression, but in reality, the term regression is the name of a technique, but people have started using the word regression to mean prediction. Now, prediction for continuous value. So anyway, we'll start using that. The first question we ask is whether these two values are related to each other or not. Only if there is a relationship, then we can go ahead and make the prediction of one value based upon the other. to check whether there is a relationship between these two variables or not, we use this quantity called correlation coefficient, which is nothing but the average of the product of the standard scores of these two variables. Okay, standard score for x, standard score for y. So product of them and average of those. Okay, average of this product is what is called the correlation coefficient. Correlation coefficient is a number that lies between -1 and +1, and without saying implicitly, the correlation coefficient as described here is valid only when the relationship between the two variables is linear. Okay, so correlation coefficient lies between these numbers -1 and +1. When the correlation coefficient value is close to -1 or +1, then we say the relationship is strong. When the correlation coefficient value is close to 0, we say the relationship is weak. And when the correlation coefficient is negative, what that means is, as one variable increases, the other variable decreases, and vice versa. When correlation coefficient is positive, then both of them increase or decrease together. That is, as x increases, y also increases, or if x is decreased, y also decreases. Okay? So that's what the sign of the correlation coefficient imply. The magnitude of the correlation coefficient tells us the strength of the relationship between these two variables. We started with the example of grocery delivery time based upon the distance to which delivery is made, and we've calculated that the correlation coefficient for these two variables happened to be 0.9. So we figured that it's a fairly high correlation coefficient. The relationship is strong. Therefore, we could go ahead and start exploring the relationship between these two variables. What if we start with the idea that there is no relationship between these two? Okay. What if we were to start with the idea that there is no relationship between these two?
Hi everyone, welcome
Then,
back.
The best prediction we can give
After the
is
enthusiastic
the
discussion last week,
average
during the
value for
session,
the y variable, irrespective of whatever be the x variable.
we couldn't get
Right? Irrespective of whatever be the value of x
or
variable,
Upgrad to agree
the prediction we will give
for
the y variable will be the
any
average of the
extra
values
classes.
for
Two
the y
reasons are
variable.
cited.
So when we do that,
One was
the
that
errors we get
we don't have
is called the
any
set of errors that
room
we
to
get
play
are called
at the end of the
total
course.
errors,
So
and
extension
we
beyond
quantify the
the
errors we get using this quantity
prescribed
called
final
sum
date
of
is not
squared
possible.
totals,
That's one
SST,
reason.
which is essentially the
And the second reason,
sum of
we were thinking about
the
having
measured value minus
an extra
mean
session
y value,
during
the whole square.
the weekdays.
So this is the sum of
And
squared
even that
total
was
errors. Then what we
rejected
did was,
because
okay, this is what we would get
they were
if we do
worried
not
that
assume a model.
some
But
during the weekdays,
when we assume a model,
few may be
then
able to attend,
we go
few
for
may not be able to attend,
a model
and
which
hence
is called a linear model,
they
which
said
has a
that
form y
that's
hat
also
is equal
not
to beta
possible.
naught plus beta 1 x.
So I was
where
told
y hat
categorically
is
that
the
I
predicted
better
value,
finish on time,
and beta naught and beta 1 are called the
or
parameters
on
of
the
the model.
scheduled, complete all
Our task
the
is to find the values of
topics on
beta
the
naught and beta 1
within the
such
scheduled
that
dates.
the errors we
The
have
only
with the model is minimum.
room I was given to
So what
play
happens
was
when we have the
I could
when we have
extend
the
the
model,
sessions
then we would have
beyond the
errors
2 hours 45 minutes
which
limit,
are hopefully
which
smaller than
I think
the errors
I
we
will
found in
have
the
to
total
do,
errors,
because otherwise
and these errors are called
we
residual
might
errors,
not be able to
because these are errors that are still there even after building the model.
do
And
much.
we
My memory is today is the
quantify
10th session.
the quality of the model by looking at the sum of squared errors, okay? The sum of squared residual
after this, I
errors,
have only 3 sessions.
which is
there are too
yi
many
minus
there
yi
are too
hat for
many
each data point. We
lab
make a
sessions. I'm
prediction.
not sure. I
So
hope
that's called a yi hat.
those
And
lab
then the
sessions
difference
are
between the
useful.
measured value and the predicted
But
value and square of that, and sum over all values. That's
I
called
get a
the sum of
feeling
squared
that
errors. Okay, and this is called the sum of SSE. We call it sum of squared errors, or
we
sum
will
of squared
have to
residual
rush
errors.
in
And
the next 4 sessions
we
starting
saw
today.
that
Okay.
for
So
this,
how with
for
that
problems of this kind, namely,
said, what I
that
am
when we
going
have
to
only
do is
one
I'm going to
dependent variable, these
turn
kind of problems
on
are
the
called
complete
simple
lecture mode.
linear regression models.
of course, I don't want to
It is
kind
easy
of
to determine the values of beta naught
completely
and
turn
beta
off the
1.
discussion
That is,
mode.
the parameter values
Okay,
can
so
be very
we'll have
easily
some
determined.
discussions, but let's try to cover as much ground as possible in the next 4 sessions starting today. Okay, so in the last session, and that's why usually I wait for about 5 minutes for the quorum to be reasonable, but today we have
These,
only about 15
These
or
parameters
16
can be
people
easily
now.
determined using calculus
I-
for a simple
So
linear
people
regression
might
problem.
be slowly
But
joining in.
in general,
So I'm not going to
when
wait
we
for
have
them.
more than
Just
one
start the session
independent variable, which you
and
will see pretty soon,
continue from
either
where we
today
left off
or in the
last
next session, that is
session,
tomorrow.
last weekend.
When you have more than 2 parameters,
Okay.
or when you have more
So
than one independent variable,
last
now doing
weekend,
calculus
the last session, we
is not
studied about
difficult.
multiple linear
I mean,
regression.
sorry, it's not impossible, but it's quite
And
difficult.
we
because very
covered
tedious.
two very
So what
important
people generally do is
ideas
resort to
in multiple
numerical
linear
methods.
regression.
And the numerical
Namely,
method essentially
how
means
do
that
we
you
deal
start
with
with an assumed value for beta naught and beta 1. With those values, make the predictions, calculate the errors. Now go ahead and change the values of beta naught and beta 1 by a small amount called the step size or the learning rate. And then what you do is find once again the sum of squared errors.
We also dealt
and
with
see whether the sum of squared errors
very
has
important
decreased
challenges
or increased.
when we deal with
And if it has decreased, then you know that the previous value was
that is
not the
when you
minimum.
have more than
Therefore,
one
you start with the new value and then repeat the process again.
problem.
As long as now the sum of squared errors keeps decreasing.
The most important,
and once it has plateaued,
actually
or once
we
it
covered
starts
all the three.
increasing, then
The
what you
most
do,
important
you step back and
challenge
say that
is
that is the minimum
the true
sum of squared errors
independence
that I can
of
get,
these
and
independent
whatever
variables.
values of beta naught and beta 1,
right?
that are
Even though
resulted
we
in
call
that
them independent
sum of
variables,
squared
it
errors
is not clear
will
whether
be
they
the
are truly
optimal
independent
parameter
of each
values.
other or not.
And I
Therefore, we decided we
and
will
I
come
kind
up
of
with a test.
alluded to you that there are two
to
issues here.
check
One
that.
issue is
And
the
what
step
we
size or
did
the
was
learning
we
rate.
came up with
You know,
this
how
idea
big should I
called
change? How
variance
large should be the
inflation
change?
factor.
Or how small should be the change in the values
This
of
is a method by
beta
which we
beta naught
check
and beta 1 or the parameter values.
for every
And the second thing
independent
we discussed
variable
was, should I increase or
whether
decrease the values?
it is
Okay, so the magnitude
multicollinear
of change in the values of the parameter.
with the
That's
other variables.
That's
That
a
is,
question.
whether
And the
that
direction of
variable
change,
can be
that's another question.
expressed as a
The direction
linear
of change is addressed by a
regression of
technique called gradient descent,
the
which you will
other
see in the next.
variables. And how
hopefully
do
in
we
the
do
next
that
session,
for
or
each
if,
of these models?
depending upon the
For
time
each of these variables,
today,
we build
maybe we'll
these
see it today.
models.
Okay.
And
So
for each of these
the direction
models,
of change
we have R
is
squared,
given by
and
the gradient descent
a
technique.
non-linear function of the R squared
The
is the
magnitude
VIF.
of change
VIF is equal to
something that
1
we play
over
with.
1 minus R
And
squared.
since that's
So when
something
R
that's not
squared
fixed
is
by the optimal
0,
and that magnitude of
VIF
change,
is
that is the
1.
learning rate or the
No,
step
that
size,
is very
is
poor.
something we provide to the
Very
algorithm.
poor or
We
no
call that hyperparameter. We call that hyperparameter.
correction of
Now,
the total errors.
With this,
Okay, that means
unfortunately,
it
this
is
numerical
not
method
a,
also
it's not a
involves
good
calculus.
model.
Okay, it
That means
involves
this
the
variable
calculation
is
of what
not
is called
dependent upon
the
any
derivative.
other variable.
Okay,
Right?
and that's called
But
gradient.
when R squared is
so
1,
the derivative. But anyway,
then the denominator
so we
is
saw
0.
for the
Therefore,
simple linear
VIF blows
regression,
up,
we saw the
goes to
formula
infinity.
for calculating
Therefore,
the
we
slope
set
or
some
the strength
value
of relationship
intermediate,
or the
VIF
slope
of
intercept
4,
for the
Y4.
independent
When you
variable
set
and
R
the
squared is equal to
constant in the model, beta.
0.75,
and using this
then the
model,
denominator
right,
becomes 0.25.
using these values of beta
Therefore,
naught and beta 1,
VIF becomes 4.
we have the
So,
model.
R squared
And,
is 7.
We saw that
75%.
with this model,
That
we
is
have two kinds of
about
errors now.
75% of the total
sum of
errors.
squared residual errors, which
If it is
when we have
corrected,
a model.
then we
When
say
there is no model,
there is
we have
a
the sum of
strong
squared
relationship.
totals.
That means that
Okay, so these two
variable,
kinds of errors
which
are
has
solved.
an R squared
When
value
we have
of
the model and
0.75
then
or
we
greater,
remove the model,
is said to
we say
be
the errors regress
multicollinear
back
with
by
other
some
variables.
amount. They go back to the worst situation.
R squared is equal
by
to
some amount.
0.75
And
means
the amount by which these
VIF
errors
of
regress back
4.
is called
So
the regression
VIF
errors.
of
Yes,
4
Chandrasekhar,
is
please go ahead and ask
usually
a question.
considered
So when we're looking
as
at
the
the sum
threshold
of the
for
total errors,
determining
right?
whether a
So there
particular variable
the red line below
dependent
20,
upon
is
or
that also counted as
multicollinear
part of the
with other
total? Does it
variables.
start from here?
Yes, yes,
Now,
everything. For every data point,
if
we do this.
we are very
For
lenient,
each data point, we calculate this difference.
okay,
Some
that
of them are
means
positive,
we
some of them are
want very
negative.
strong
Therefore, we have
evidence
to
of
square them to
dependence.
get a
That
good
means
estimate.
R
So that's
squared
why we have
value should
for
be
all
very high,
points.
All the data points. Okay,
all
thank you.
data points.
right? So when the
Same
R
thing with
squared
sum of
value is
squared
very high,
residual
that
errors.
means we are looking
Same
for a
thing for
very
sum of
strong
squared regression
relationship.
errors.
That means uh,
And
we are
without
very
any
lenient about
mathematical
this multicollinearity.
proof,
Okay,
I
that's
told
what
you
it means.
that
So it's a counterintuitive
in the squared sense,
argument.
total errors
Okay,
is equal
even
to
if the dependence is
residual
fairly strong, let's say 0.8 or
and the
0.75
regression errors.
R squared value.
Okay. Total
I'm
errors
going
in the squared
to
sense.
still
That is, sum of
consider
squared
this
totals
variable to be
is equal to
independent of
sum of
others.
squared residuals.
That means
plus
we are
sum of
very
squared
lax about
regressions.
this interrelationship.
Now,
That's
from
what it
this,
means, right?
we derived
So
a
as the R
quantity
squared
called
becomes
R squared,
large, or
R
as
squared
VAF becomes large,
called the regression
that
coefficient
means
is
we
nothing
are
but
very lax
the
in
proportion
our
of the
criterion
total
for
errors that
independence.
is explained by the
But
model.
if we set VAF
Okay.
to be smaller
So
number,
SSR is the explained errors.
let's say we set
So
VAF
what
to be
proportion of the total errors is
0.5,
explained by the
sorry,
model? That is
R
called
squared to be
R
0.5.
squared, and it's
That
called the
means
regression
VAF
coefficient.
to be
So
2.
there are these two formulas which you can use.
That
The
means
second one,
even
the
if
light green,
the
is the one that's usually used.
R squared
Because
value is
when we don't have the model,
0.5,
we calculate sum of
we
squared
say
totals.
that it's a strong
When we build
relationship.
the model, we calculate
Therefore,
sum of
there is
squared
multicollinearity.
residual errors.
Therefore,
So
this variable
from
has
this,
to be
we can
dropped
calculate
off.
R squared.
That means we are
straightforward,
very stringent.
using this 1 minus SSE
Okay.
over SST.
So as VAF increases,
Now,
that means we are very lax
we
in
saw
our
that for reasonable models,
in our
R
independence
squared lies
condition.
between
That's what it
0
means.
and
Okay.
plus 1.
So
Both 0 and plus 1 included.
with this
Extremely
VAF,
rare
I
cases,
think
because of the way it's given here, R squared could get negative, in which case you will have to
you could play with
take a step back
these
and check multiple things. See whether your
examples.
computations
But
are
then
correct. See whether
many a
your
time,
model is
what
sufficient
happens
or what.
is,
Lots of things you may have to go and check.
when there is a large number of
So when the R squared is
not
close to
necessarily
0,
large number of variables,
that means
but
the proportion of the
many a
total
times
errors that has been explained
not
by the
be
model is very low. Therefore, the model is a
meaningful,
poor model.
or it might
When R squared is close
it
to
might
1,
not give us a
the
very
proportion of the total
clear
errors
idea
explained by the
of
model
how
is
to
quite
go
high.
about proceeding to check
Therefore, this is a good
VAF
model.
or any other methods.
And
Okay. And
kind
in
of,
these situations,
foretelling
what
that we are
people
going
do
to
is
use
people go
multiple
to a classic
independent variables.
technique
I
called
said that instead of using the
multi-stage
sum of squared
model
errors,
building
sum of squared
exercise.
totals, why not use
Okay.
the mean
So
squared errors?
I'll
and mean
describe
squared
what
errors?
that means.
And when we
using
do that,
this particular
we
example,
know that mean has to be determined
what we are
based
going to
upon
talk
the degrees
about
of freedom.
is what is
And for the
called
sum of squared
a
residuals,
stepwise regression.
the
Okay,
degrees of
stepwise
freedom
regression. So we are
is
going to
n
go
minus
step
1.
by step.
Okay, because
To do that, let's
sum of squared totals,
start with an example.
the degrees of freedom is
Okay, here's
n
an
minus 1 because
example
we
of
lost 1 degree of freedom when we calculated the mean.
world oil output
For the sum of squared residuals,
okay.
the
Whatever
degrees
units,
of freedom is
okay,
n
this
minus
might be
k
in,
minus 1. We lost 1 when
millions
we
of,
calculated the mean,
barrels
and we lost k
per
degrees
day.
of freedom when we calculated the k parameters.
Okay, few years ago.
So n minus k minus 1.
And
Therefore,
since US
dividing the
is the
sums
major
by the
consumer
appropriate
of
degrees of freedom,
energy,
we would get the means,
no?
and the
So
corresponding R
we
squared
wanted
value
to see
is
whether
called the adjusted R
the
squared.
world oil
It's
output
called the adjusted R squared.
can
And
be
this is what
modeled
we would
just
usually
based
use.
on the
This is what we would
US
use.
energy indicators, energy consumption
There
indicators.
is another.
Say, for
I asked
example,
this
how much
question.
energy
I do not know
overall
whether you had a
the
chance
US
to
households use
take a
in
look at
some
this
unit, British
question.
thermal,
Let me go and
millions
check
of
whether,
British thermal units, I think. US auto fuel rate, US nuclear production rate, US coal production rate, and US dry gas in whatever units, some different units. Okay, let's not worry about the units. But these 5 variables related to the US energy
I did not write any question.
production
on
and
this,
consumption.
on
We
this.
want to see whether we can use
But
this to
let us ask
model
a simple question.
the
Okay?
world crude,
The
crude
model
oil
that we
output.
have is this.
Okay, and here
Time
is
to deliver
some
for
sample
that particular
data.
example. The model we ended up with was time to
Now,
deliver was
how can we go about
4.8
doing this?
plus
Very simple.
0.04
You could
times
build
distance.
multiple linear regression
That is, when the
model as
distance
before
increases by 1 meter,
and check for
the time to deliver in minutes increases by 0.04 minutes.
multi-collinearity of each
That's
of these
right.
variables.
That's the
Each
meaning
of these
this
variables
quantity here.
is a
4.84.
continuous
What is the
variable.
meaning of that?
Therefore, we
That's
don't
a
have
constant.
to worry about
Okay. That means
dummification
even when the
or
distance is 0,
anything we deal with
in math language we would call that
categorical
the y
variables. So we
intercept.
don't have to worry about
So
them.
when distance is 0, the time to deliver is 4.85 or
Apps
5
have
minutes approximately.
real-time access to
Okay.
your information.
What does it mean?
In this meeting?
I am at my grocery store and I'm
Whatever
delivering
that
that.
means.
Okay, I'm
Okay.
delivering that. Okay. How much time should
What
we
you could
expect for
do
that?
is, in fact, you could think that something
We
might
would
be
have
interacting.
0 minutes to
Some
deliver.
of these
Why
variables
would I
might
take
be
any time to
interacting.
deliver
So
to
you
my
could
office?
bring
I'm
in
right here. Everything is around
interaction
here.
terms and
Right?
do the same
In this
exercises
situation,
as we had done before.
this coefficient,
However,
different from 0, is a meaningless
However,
quantity.
okay, I can see what's the chat.
Right? Beta naught
messages.
in our model.
However, what we'll do is we'll first start with this simple method. Simple, these 5 variables. Okay. And we are going to do what is called stepwise regression. What is stepwise regression? We will start with a very
situation,
simple model.
For our example,
We will use
this
only
beta
one
naught
variable.
has to be 0. Okay. Because
We'll use only one
when the
variable
distance
to
is
model
0,
the world oil
time to
output.
deliver has to be 0.
So
right?
which one of these
So how do we
variables
deal
can
with
we
that?
use to model?
We deal with that by a simple
That's a
technique
question.
where we say,
So what we do
force
is
beta naught to
we
be 0.
go ahead and build 5 models.
Let me demonstrate that. Let me go back here.
One with
start a
US
new
energy,
generation,
one
like
with the
what we
second
did last
variable,
time.
one with the third
I'm
variable,
going to start
fourth variable,
doing
fifth
this,
variable.
Go to data,
Okay,
do
5
statistics,
models
and do a
we
regression
build.
here. And I'm going to start.
And then what do we see?
Where are the independent
We see
variables?
which of these
Service
models does the best.
here.
Okay.
And
So what do you mean by does the best? We can do, we can use
here,
what shall I call it?
say both
We
of them
could
have
use
been
R
done.
squared
This
value.
has to be printed where
That's one thing.
I want this.
Or we could use the
here.
P value
And
or
if you
the
see
T
here,
value,
okay,
student
last
T
time
value for that
left
particular
everything to
variable.
be,
We
by
could use
false.
that. There are
So grouped by
multiple
columns,
different
ascribed linear regression,
ideas people use.
confidence interval, which
Okay.
is 1
So
minus
you
alpha,
have these
which
5
is 0.95,
models,
that is fine.
and of these
Calculate
5
residuals, I don't want
models,
this, I don't want to calculate
choose
residuals.
the best one
Force intercept to be 0.
using whatever criteria
Right?
you
This is
use.
usually an option. This is called
Okay, choose the
regression
best
through
one.
the origin.
Now what you do
So we
is,
are going to
let us say
force the intercept.
we find that
0. That
US
is, we are going to
energy
we are going to
happens
force
to be
beta
the
naught to
best
be 0.
best.
And
That is
with
world
that,
oil
then what we have only
model
one model,
as
only
US
one
energy
parameter, beta 1.
is the best
Right?
model among
And
these
then
5
we will
models.
see whether
What are the 5 models? World oil model as
changes.
US energy,
Of course,
world oil model as US auto
these
fuel
are,
rate, world oil against US nuclear, world oil against US coal, world oil against US dry gas. Out of these 5 models, world oil against US energy, let's say, turns out to be the best one. Now what you do is take that model, add one variable to that model. So now we have 2 variable model. Okay. So how many models we will have now? We'll have 4 models now. US energy and US auto fuel rate, US energy and US nuclear, US energy and coal, US energy and dry gas. Okay. Now see,
so when I do that,
which is the best out of all these 4.
Okay. So now what I have done, here is a model where y
and
is equal to
the best out of this, see
beta.
whether that's still valid. What do you mean by that? Whether P value is still greater than alpha,
not y is equal to beta naught
whether
x,
R squared is reasonable, whatever numbers you are looking at.
Right? And let us see what has happened to R squared.
Let us say US coal turns out to be the
bit
model. Okay, so
earlier
world oil
0.900
modeled against US energy plus US coal.
Earlier, the R squared
now what you do?
0.8.
Go ahead and add the third variable.
Right?
What will it be? US energy, US coal, US auto fuel rate.
But now you
US
see
energy, US coal, US nuclear, US energy, US coal, US dry gas.
In this case, that's what, right? And
see which is the best model out of these 3.
P value you see,
and see whether this model is usable. And if it is, continue this process.
If P value is practically 0,
and this kind of process,
what is this?
Is called
analysis of variance tells you. Analysis of variance tells you
stepwise regression.
The model.
Okay. So here are the units given.
The predictions of the model are no different from the predictions without the model.
Nuclear.
That's what energy means. Therefore, the P value for that hypothesis is 0.
Seems to be wrong.
Practically 0. Therefore, we reject the hypothesis, which means
maybe it's very small.
The model is
not even in megawatt hour. So
and now look at the coefficient.
Coal based.
The coefficient also earlier it was
total dry gas in cubic feet.
845.
Not in cubic feet. Cubic
now
kilo feet.
Maybe. Now look at the coefficient. Coefficient is very different. 0.05.
Fuel rate of US owned automobiles.
Intercept is 0.
Okay,
which is what we forced.
So this is the fuel efficiency.
And the coefficient is 0.05.
All these variables.
Okay. Earlier it was 0.04.
So this is what we do.
Now it's 0.05. Slight change in the slope.
So here is
slight change in the slope.
First step. So world oil and 5 models. One with US energy, one with the nuclear, one with US coal, dry gas, fuel auto fuel rate. Out of these, see which is the best model.
This,
you could use R squared,
blue line, which
or
is
you could use the T value.
Just shift a little.
The larger the T value, the farther away it is from 0.
That what has happened is,
right, and 0 is our hypothesis.
Actually, yeah.
So choose the T, which is the largest value.
Let me see.
So in our case, this becomes the best model. So world oil model against US energy. Now what you do is add the second variable. So whatever that model is, this model happens to be 13.075 plus 0.580.
The
times
dotted blue
US
line
energy
is the
is the
vertically
world
shifted.
oil
I just
output.
moved the original model.
Now to this,
No, just
let's
set
add the
beta
other
naught V0.
4 variables one by
I did
one.
not change the slope.
US
If
nuclear,
that was
US
the case,
coal, US dry
I
gas,
would have
US
gotten
autofuel
this
rate.
dotted blue line.
And we do this and build
Okay.
the model.
But when I
See which is the
refitted
best
model,
one. Here there are two
by
contenders
forcing the
which are
beta
very
naught to be
close by.
0, the intercept to be 0,
US
I
nuclear
got a
and
slightly
US
different
auto
model.
fuel
You see,
rate.
the slope has changed, slightly different model.
90.8,
And the slight
90.06 R
difference,
squared.
what has it done?
Minus
it has actually
3.75
improved
to
my
the left side.
my
Minus
model performance much
3.60
better.
to the left
Right?
side.
You can take a look at this.
So
For
which
example,
is farthest away
mean
from
squared
0?
residual error. Okay?
When you look at
Mean
T,
squared residual error.
that's again
Originally,
minus 3.75.
the mean squared residual error was
So US energy and US
47.73,
auto fuel rate,
but now it is 55.
they happen to be
it is actually
the
slightly worse at the
best
best residual error.
model
Okay.
out of
But,
these 4 2-variable models.
Even though it has worsened a little bit, this is
and T value
this actually
still everything is
physically meaningful.
below
physically meaningful.
0.05.
The
Therefore,
model
we
is
cannot-
performing well on all.
So we reject
parameters
the null
that-
hypothesis.
Right.
Null
So
hypothesis
this is one thing that you have
model
to
is not
check.
useful or
Yes,
this
this got
variable does
considered.
not contribute anything.
Sir, from a practical
So that's the null hypothesis.
sense,
We
right?
reject that.
So
Now to this,
only if the
you add the
activity is
next-
initiating from the
you add the
origin,
next
that's when
variable.
you
so US
do not
energy, US
consider the
auto fuel rate,
y-intercept.
add
Is
US
that a
nuclear, US coal, US
fair
dry
statement?
gas. And
And,
look at the P values for
And
all
if you
of
look
them.
at let's say a delivery,
all
and
of
then
them
in this case,
happen to be
and someone is picking up the
greater
order
than
from the
0.05.
destination itself, okay, that y-intercept
does it
will
mean?
in reality
We
some
cannot
will
reject
always
the null
exist, isn't it?
hypothesis
From getting it
that
from a storeroom
the
to the
effect
gate
of these
or
variables is zero.
to the
Each one
front
of them
counter
independently
to hand over.
zero.
So just practically, I'm thinking that is it like
Right.
will ever be zero?
So what does it mean? That means the
well,
best
that's the
model
kind of interpretation perhaps you will give
is
for
this one.
The
That
original
is
model.
world oil output
Okay.
modeled against US energy
So I'm just giving you
and US auto fuel
you,
rate.
you have a very good question. Say for example,
This is the
came to
kind
pick
of
up the brochure, right.
approach we
So
take
for
when
your delivery person, the distance
other
this person travels
methods,
is 0.
like standard methods like
But then there's a small
using,
time
VIF
involved, even for delivering at the
it's not
at
giving
the
us
warehouse
any
itself.
clear
There is some time involved, and that
idea of what is
time
happening.
is what
So
this
this is a
intercept is.
very, in
That's
fact,
the kind of
what I
interpretation you want to do.
find
That
is
makes sense.
in many
But thanks
domains,
for
especially
giving
in
this
the
interpretation.
medical
I will probably use it in my
side,
future class.
no,
Sure, sir. Sir,
see,
just an additional
people
point on
straight away
that.
go to
So let's say that we use a ride share to
in
book the
fact,
cab, right?
I would be
And
surprised if
the
many
distance
of them
usually
have
is
even heard of the term.
it's covered in two parts. One is
VIF,
for the ride
right?
to arrive to your destination,
So
and the second is from a
this is
destination to
the
wherever you are,
general technique.
to your home,
Yes,
to your
Sam,
place of
yeah,
pickup,
please go
then
ahead.
from place
Yes,
of pickup to
Professor,
your
how
place of
did you
drop.
get
Okay.
7.14 in the equation?
Are there two separate models used there, or
Yes. Yes.
Okay.
See, when you
This is
put
the
these
model
two
only
variables
for,
here,
from
you
the
are using US energy and
warehouse
US
to
auto
the
fuel
place
rate,
of
right?
place of
So you use the data, use this data and build that model.
Yes.
Okay.
Build the model with these two variables. When you use only these two variables and
So,
build the model,
At this point,
for
that I
beta
have been
naught, we
talking
get
about
this
for the
value.
past 10 minutes is essentially to introduce you
For
to
beta naught,
Ah.
the idea of
Okay.
regression
okay. When this second variable is not added,
through the.
of course things are different.
Okay, so that's
Right.
what
Beta naught is
is another
different.
technique. If you
But
hear
the
about
moment you
this or
bring in the
see this
second variable,
somewhere, just
the
understand that
constant
you are,
changes
setting
because you're going
beta
to a
naught
higher
be
dimension.
0 and then
Constant
picking only
changes.
beta 1.
Okay.
Right.
And
And,
that's why it becomes 7.14.
If you see
and
the
it's, this is the coefficient for the second variable.
the degrees of freedom
So
also
as
vary
the
in this case.
fuel efficiency
Okay.
goes up,
for
the world
regression
oil output
for
decreases.
this,
That's why the negative
when we
sign
have regression to the
here
origin,
tells you.
the degrees of freedom are for regression
Auto
is
fuel
1
rate,
because we are
that's the
removing
fuel
only beta 1.
efficiency.
And
The
for
fuel
residuals,
efficiency
it's
is
given as
high,
24.
then
In this case, you would see
the need
1
is
and
lowered.
23 for the
Therefore, the
residual because we
production
have the
goes
two
down a
parameters,
bit.
beta naught and beta 1.
Okay. Likewise, when the
So,
US energy consumption
Anyway,
goes up,
so
world oil
what we
output
will do
also
is
has to go up. So you
this
have
is all
positive sign here.
the
So these
basic
things make
mathematics behind it.
sense. In
Now
that
we
sense.
go to
Yeah,
a
thank
much
you.
more a deeper analysis.
We could do the
And
same thing
I asked for some observations in the last session.
in the
And
reverse
we did
direction.
indeed make some observations.
Okay.
One of the observations.
So what we could do,
made
we could
was
start with
that
put all the variables
for a given value of
in the model,
X,
all the 5 variables in the
that is
model,
for a single value of the
Okay.
independent variable,
and
we found
see what
multiple
happens. You find
dependent
the R
variable
squared
values. That is
for the model,
different
F statistic
customers
for the model,
at
whatever.
the same distance from
Then what do you do?
the warehouse
then
or from the grocery
Remove
store.
one variable.
They had different
So second
delivery
step,
times.
You
and we
you
argued about
remove,
it, why that could be.
you
You
get
many reasons.
5
Here we are not going
4
to worry
variables
about all these
models.
reasons because we just have this data.
Okay, you have removed one
This data,
variable,
what can
you have
we
one
observe,
model,
what can we do
another
with this?
variable, another 4 variable
So,
model, so on and so forth.
The first observation we
And
made was
see
for a given
which is the best one
value
here.
of the
And see
for a
whether the
single
best
value
one
for
here
X,
is better than the previous
multiple
one.
values of Y are possible. Sorry.
If it is,
multiple values
then
of Y are possible
repeat the
in
process.
the data.
From the
Okay,
best
that's
one,
one.
start
Okay,
removing
I
one
probably
variable.
went ahead of myself. There are a couple of things that we want to talk
Repeat
about
the
before we do
process.
this. Okay.
Whenever
So this we already talked about.
there
This
is
is what
no
the F
improvement,
statistic is all about. ANOVA.
no, you
We
go to the previous
hypothesized that the
step
model
and
did
choose the
not
best
perform
one
any
there
different
and use that as your
from
mark.
just the mean prediction.
Okay.
So we state this using the
Okay.
H0, which is the null hypothesis and alternate hypothesis. This is the null hypothesis did not perform any different from the mean prediction.
So
But
that is
it performs better than different from the mean prediction. That's the
that is
alternate
the
hypothesis.
stepwise
And this
downward
is captured by the
regression
F
model.
statistic,
Okay,
like what we
stepwise
saw in that ANOVA.
downward regression.
Right.
Okay.
So F is
So
I
either you can go
F is the
upward
ratio
or
of
you
two
can go downward.
variances.
Usually
The
what
variance
happens
at
is
the
many
top is
of
always
these
a bigger number than in the
software,
denominator. So
they do downward
we
regression as a
expect the
standard
value of F to
when
be
you
greater
use
than 1.
stepwise regression.
So the null
They use
hypothesis
downward
when we
regression
define
as
F this
standard.
way
And
is that F is equal to 1 is
no,
the null hypothesis.
this is
And
commonly used.
the alternate
As I told you,
hypothesis is
in
since
the
the
medical,
reality F will be always greater than
clinical
1, the alternate hypothesis is F is
and
greater than
biological
1.
sites,
And with that,
I've always seen
we-
people use
other
stepwise
things are the
regression
same,
whenever
like
you have
alpha value,
multiple
rejection,
variables
gradient, everything is the same.
the data.
So we do that.
So in
Once
summary,
we have done that,
finally,
we
what I would
also
like
see
to
there is something called the
end
p-value for the parameters.
linear regression. That
Even
is,
for
we
the
are
model
actually
parameters, we have the p-value.
closing.
Okay, and it says something called the p
Maybe
statistic.
not, maybe not.
So what is it? This is
We are
essentially
closing the chapter
we ask the question, okay,
to some
the
extent
model is agreeable.
on
Now,
linear
are
regression.
all the
That is
parameter values,
prediction
are they
of a
also agreeable?
value.
Or some of them
Okay, prediction
actually
of a
0.
value. Value means
Some
the
of them.
continuous variable. Well, value of a
So what we have to do, we have to check for each
continuous
one of
variable.
these parameters.
And
We will have to do
that is linear regression.
statistical hypothesis testing.
So what do we do
So what
when
do
we
we
have
do?
a linear
In
regression
this case,
problem?
we
This is the
assume,
kind of
okay,
algorithm
this,
you can
this is where the
say
population
use.
and the sample
Yes,
idea
Prince
come
Dubey,
into
please
play.
go ahead.
So we have
Am I audible?
some data.
Yes.
This data, we imagine this to be a sample from a
Now you are
population.
not.
Okay, population of all distances and all delivery times. From that, we have taken this small sample, right? And in this, so now
Prince
we ask the
Dubey, if
question
you are speaking,
with this. So with this, I got this
I cannot
value
hear
for
you.
the parameter. Okay, so this you can think of as the population sample mean, right? Now with this, I
Okay.
make a null hypothesis
Am I audible now?
that
Yes,
the
you are. Please go
actual
ahead.
sample
Okay.
mean
So for
or
this
the
step
actual
by
parameter
regression,
value, population,
I
the population parameter
in case
value
if
is
I'm
0.
having a data where most
Okay,
of
that's
the
the hypothesis
columns
I make.
or
And
most
now
of the
I ask the
features
question, okay,
are very
this
much
is
correlated,
my
is it as advisable
my
with the step by
coefficient. This is
regression?
the coefficient I have. Okay, this is the coefficient value I have. Now,
If you know
with this
beforehand
data,
that these variables are
can I
correlated,
reject
of course, I
my
would
null
say
hypothesis
don't
or
do
not?
that.
And in this case,
Okay.
then we will
Okay.
do what we
So
do, like what we did
basically,
in the
sir,
normal
in
distribution.
finance, we never used it
Except that we
before,
are
but
sticklers for some details.
predicting
And the
the
detail that we
returns
have
for a
is,
particular stock,
in
I
reality,
see a
okay, what
very
do we
huge
do in
potential
normal
of
distribution? In normal
utilizing it.
distribution,
Although
when we
I
did the
never used
hypothesis
it
testing
before,
using
but I'm gonna
standard
use it.
normal distribution,
But
there
there are
was one
certain features which are
underlying
very much
assumption
correlated,
which I
very,
did
very
not make
highly
explicit.
correlated. That's why
The
I
underlying
was
assumption that I
checking
never
whether
explicit was that
Never use that
the
because
standard deviation
let's say as you keep
for
adding
the
more and more
population.
variables,
Mhm.
what
The
would
data, I
happen
have the
is
entire data, and if I take the standard
artificially
deviation,
the
remember those
performance
200,000
would,
apples.
improve.
Okay, and the 200,000 apples,
Mhm.
You know,
for
when
those,
they are
I
correlated,
have the standard
instead of
deviation of the
using the
weights
variable once,
of all these 200,000 apples.
you would be using the
If I know
variable more
that,
than
then that's
once.
called the population standard deviation. Okay.
Yeah.
And
Right.
the assumption we
So,
made there
that would
was
be
that,
counting the
yes,
effect
we
of a
know the
variable
population
more
standard
than
deviation.
once. So that
That is the
will
assumption we
improve the performance
You can ask the question, no, we never had the population standard deviation value.
artificially.
So where was
Therefore,
that?
this
The second
stepwise
assumption
regression,
we
I
made,
would suggest
another
only
implicit
when
assumption we made was that
you
the
don't
sample standard deviation was the same as the population
see
standard
any
deviation.
clarity. You know, your
Okay. That was the
VIF
second assumption we made.
is not showing.
With these two assumptions, we could
any
go ahead
clarity.
and
In
use
fact,
the
if you
standard
check
normal
with the
distribution.
empty cars data,
But
my
in
memory is
1903 or
that,
something like that, about 120 years ago,
every variable
this
will fail the
statistician,
VIF test.
I forget his name.
Okay.
I mean,
Okay. So,
Gossett,
but the model
some Gossett,
itself
G-O-S-S-E-T, Gossett.
is significant.
This person
The
was
F
working for
statistic
Guinness
will give you a
Brewery,
p-value less than
the beer company.
0.05.
And what he did
But
was he
every
questioned this
variable
assumption
no
and
will
started looking
have
at the situation where
p-value greater
we do
than
not know the population
0.05.
standard deviation. If we do
And
not
if
know
you
the
check the
population standard
VAF of
deviation
all the
and we have only
variables,
the
almost
sample standard
my
deviation,
memory is
what should we
all
do?
of them has, or maybe
He
one,
did some mathematics, some complex
I don't
mathematics,
remember, but one at the most,
and then
or two.
he came to the
Everything
conclusion
has
that
VAF
instead of using
greater than
the
4.
standard score, what is the standard score?
So you will have to drop
Z
all the variables.
Was
so that
something
becomes
like,
very
what is it?
confusing.
X
It's very
sub
difficult
I
to understand what is
minus
happening.
mean of X,
Therefore,
okay,
in
the whole
those
divided by
situations, okay,
standard deviation
you
of X.
usually try
Here,
this
the
type
standard
of
deviation of X was
stepwise
the
regression,
population.
and then
Population
what
standard
happens is
of X.
we hopefully will end up
These
with
are
a
the
better
implicit
model.
assumption.
And and also what we do
What
is this,
this
even
gentleman did
stepwise
was,
regression,
no, we
when
cannot
we
do
reach the
that
best model that
because
we
we do not know
can,
the population standard deviation.
we
So
do
what we will do is we'll create a new
VAF
variable
again
and
on
see
the
how the
variables
variable gets
that are there
distributed.
in the model.
So he
In our
defined a new
case, for
variable
example,
called
we
T,
had
and this was
US
pretty much
energy
like this,
and
okay?
fuel rate.
Very similar to this.
Okay.
It should be small t.
So we would check whether
Use the
each one of
automatic
them
factorization
is
method.
independent of each other.
So let me try
These
this.
two are independent of each other. Okay, we'll check their correlation,
So let me finish
and
this
only
first.
if the correlation is poor, you should
So
go ahead
T
and
is equal
build
to
the model.
X sub I.
If you
minus
don't
mean of
find
X.
any
Okay.
other
Then
way,
this
in
divided
every
by
way, if it fails,
sample
okay,
standard
in
deviation
real situations,
of
this
X.
is where
And then
you would
not only that, you need one more.
the blind
This has to be the
algorithmic
sample
approach.
standard deviation has to be
Everything
divided
fails.
by
For example,
square root of
the model is good,
sample size.
but every variable is
Square root of the
is
sample size. It just see, it's a very
multicollinear with
small
every other
difference.
variable,
It's a very small difference.
and you try stepwise regression.
If you look
it
at
doesn't
this,
seem to give
sample
you
standard deviation divided by the square
any
root of the
clear
sample size.
indication of what
This is
happening.
nothing but the standard error
Then what you do is
of the means.
go add
Okay?
interaction
Instead
terms
of using the standard deviation
and see
of the
if something
population,
improves there.
he said let's use the standard error of the means of the
That's
data.
the way you would approach.
Right?
In
Once we do that,
that's very
he came up
rarely
with
the case. No, very
what is
rarely
called
the case. We are
this
going to
follows
see
this
that there is
variable.
another way of approaching
variable
this
T
problem.
Follows what is
of
called a T distribution.
Identifying the variables that would go into the model. Okay, that we have another very powerful approach.
If you see, if you look at this,
get to that
T and Z, they look very similar
next
in form.
part of today's session.
Instead of dividing by a number like 36, here we are dividing by a number like 6.
When we are dealing with
that's what it is essentially.
With the linear,
but otherwise they look very similar. Okay, therefore T distribution.
The idea is this.
Okay, T distribution.
Start with the this is
like
your pre-processing. Now you need to understand the data and any transformation you have to do. You do the transformation. Any feature engineering you have to do. You do the feature engineering.
Okay. But you see, if I change n,
what do you mean feature engineering?
Okay, one sample.
If there are categorical,
I might have
so
had
far
36.
The kind of feature engineering.
In another sample, I might have had 49.
If we have a categorical variable,
right? So the T value, even though the xi minus mean x could remain the same,
one-hot encoding.
That and even if the sample standard deviation
you can think of it as
the T value changes with respect to
in
the
a very
size
crude way,
or the degrees of freedom. Right.
So
therefore,
any cleaning the data, all these things.
T distribution.
Then what you do is start fitting a regression model.
Degrees of
freedom. Then do the diagnostics on the regression model.
Now, what happens?
What is the diagnostics you have to do? So usually we would do check for R squared, R adjusted R squared, F parameter, F statistic for the model, that is ANOVA on the model.
Different
then
from
T test,
Z distribution.
Student T test on the parameters, and then
when n is
check for the validity of all the assumptions.
Okay,
and see whether there are any
a lot of statements which are like axioms.
If it fails in any of these,
have trust
what
in
you
me.
do, it means that the model needs improvement.
But
you
if
go back,
obviously you could go and
check the data,
time and patience.
Usually what you do,
mathematics and figure this
explore data transformation once again.
When T distribution is different
check for
from
multicollinearity.
When the degrees of
add or drop variables
less than 30
and go do the model.
So my God, you have a lot of process to hide your better half that nobody understands that Blazor was
especially when the degrees of freedom becomes 30 or more. The difference between the T distribution and the Z distribution is practically 0.
Excuse me, whoever it is, please.
So what we are saying is when the sample size is large, you could calculate Z using this formula and then use that value in the regular hypothesis testing, or you could use you could determine T using this formula, and substitute in the T distribution with appropriate degrees of freedom and do the hypothesis testing. Doesn't matter which. But in our case,
so you keep
degrees of freedom are
keep improving the model.
So we have to use the
once
T
you
as
have
described
reached
here.
an agreeable state. I say agreeable.
I'm sorry about
not
this. Please excuse me for just a minute. Please.
Pass. Okay, because what is the purpose finally? The final end goal is to make predictions within your tolerance for errors, right? As long as your model makes predictions within the tolerance you have set for the error, that's fine.
I'm sorry about the distraction.
Right?
It was very important.
We are not in the process of understanding the truth.
Now, so
okay. We are not in the process of
calculated
understanding
the T. They determine the T here.
We are in the process of
and then
making predictions.
Okay. So you can take this as the mean value.
If that is the goal, then the moment you reach the agreeable model, you can go ahead and deploy the model.
And then,
so once you deploy the model, what happens is
find the p value. It's not over. Find the p value,
because after
now
we deploy,
check whether this p value is less than alpha.
Usually things do.
If it is less than alpha,
and where does the
support for the null hypothesis
in the data?
What is the null hypothesis? The coefficient value is 0.
With some data,
that's a null hypothesis.
We have made
support for the null hypothesis,
and then we started making predictions.
Doesn't exist if the p value
predictions are for the new data.
In
the
this
data
case,
that the model
original model
has not seen
both
yet.
p values, both parameters,
and
have
if the new data that comes in,
alpha.
when the new data starts
Therefore,
to be
we reject the null hypothesis and start using the
from the data that was used
in the
to
new
build
model,
the model,
with the forced beta naught to be 0.
Then the predictions
even then you see different. The p value is
from
much less than alpha
expected.
Right? It's practically 0,
and therefore you will start seeing that
this model is not agreeable.
Model is moving
Since
towards
the second model is physically meaningful,
non-agreeable region.
You can go ahead and use this, or as Chandrasekhar,
and we call this the model
reason. This model also makes sense physically. In those situations, you could go ahead and
different terms. But this is one of the
reasons
that
first
things will change.
We got R squared.
So what we
that's good.
Have to do
R squared
is,
being high does not necessarily guarantee the model is
we just don't
usable. We have to check for the F statistic.
Home. We
have to check for the F statistic and see whether
as soon as the model errors start, the prediction errors start increasing, and when it reaches when it breaches the threshold we had set for the errors,
statistic and see whether
what you do,
those are the model is
stop,
okay,
include all the new data
is valid. You go ahead and
put it back,
the parameters
with the older data,
see whether the parameters are also useful.
Do this exercise once again.
Okay, please go ahead.
Yes, I just want to check, is there any way we can automatically identify some of the tools that the model is, the model which we generated with our algorithm is perfectly okay, or any fine tuning is needed? Right now we are manually, determining, is it like, okay, the old, the coefficients is, earlier defined is okay, or maybe now the one which we latest defined is okay. So is there any way we can also get the tool support on this?
Of course, every
this is one of the most elementary models we are seeing.
Has all these tests
and even with this elementary model,
spit out a
continuous
saying that
refinement.
These are the concerns. These are the
continuous deployment or continual
every model does that.
And deployment.
All these software that
nature of
the tools that have been built. Remember, these are built to aid statisticians. And you can imagine now usually
as models become more and more complicated.
Therefore, yes,
move towards more and more
all we have to do is
complicated
if
models.
If you want just the report,
specifically when you
anyway the outcomes
neural network models and other types of very
thrown out like this by these
or to agentic systems
by this.
You can imagine that this thing could become a real big headache.
All you have to do is
in any kind of machine learning system, this is a small headache. So continuous
that's a very easy
monitoring.
There are two more people who raise their hands.
Integration, refinement.
Please go ahead.
Yes, Professor. So when we use Excel or Python, we get this detailed analysis. But when we use the Azure ML Studio, it gives limited exploration capability. So when we perform the assignment, we will get a RMSE, MAE, and R square. But should we have to calculate these also? Is it expected?
The technique of
yes, these are expected. I think Azure has these things. I would be very
predicting
surprised
the
if Azure
value
doesn't
for a
have this.
continuous
Okay,
variable
because they're
based
one of the
upon the
leading
values of
tools
other
for doing
variables.
this kind of model building
These
exercises.
other variables could
So
be continuous
it should be there.
or categorical.
It should be one of those, you right click on the.
So we just
model.
stop here. If you have
As
any
see,
questions,
you build
we
this
can,
using the builder,
Yeah.
and then you have these outcomes.
discuss
And in the outcomes, there should be some
for a
options
few
somewhere
minutes.
where you do a right click
If
and
not,
check
we
some
will
options.
move on to
It should be there.
next.
I vaguely remember seeing this a few months ago
change something
when I was
Already
trying
changed
to use Azure for one of the clients. I vaguely remember seeing that.
Sir, in a real life scenario,
write an email
are there
to
any ways to
if possible,
check
ask
the
them to send a
incoming
screenshot
data
of how to do
upfront
this.
before it
Maybe we
feeds
can
into
Okay, so we
the
cannot
tool
stop
where
at
the
the
model
CMAE
sits?
R square level. We should go to this level of analysis.
Check. Yes, and this is not over yet.
So this
is only maybe
see
only
what
halfway
in
through.
practical
Much
sense I've
more,
seen in my
there are
job
a
is
few more
that we don't
analysis,
have a
diagnostics we
control
have to do
on
before we are
the
confident
upstream
that
data
the
that
model is
feeds
usable.
into the models. Okay,
And that's where
and
we
there
are
could
moving
be
next.
any change that could be happening
So-
changing the nature of the upstream data.
After
Right.
this
So before the
hypothesis on
data enters
parameters,
into the model,
okay, and if everything
can there be any
looks
practical
fine,
monitoring or
now
checks be
we
implemented
go
to ensure that the
and,
right data is
ask
entering the
questions
model for what
about
it's
the
what
underlying
for the
assumptions.
purpose it is designed
Okay, what are the
for?
assumptions that we have? Awesome. Okay. Only reasonable prediction.
You have described the question
Only
very
reasonable
well, but
prediction
I'm
that
not
we
sure
can make.
whether I understood the question
Okay.
equally well. Let me
For-
tell you
so
why
very poor
my understanding is
animation. So you got the
why
answer to the question.
I
that
don't
was going to ask.
understand this. Okay.
So now the question will be, what is the question that I'm
The
going to ask?
idea
Okay,
is
now,
this. Think about this.
The observation that
You
we made
build
earlier,
the
remember,
model
for a given
based
value of x,
upon
for one
a
value of
sample
x
you have got.
in the data, it is possible to
Right.
have more
Sample
than
is
one
all the
value
historical
of
data
y.
you have collected so far.
Right? It is possible.
Okay. But that's still a
Now,
sample of what
the
is
question
possible
is,
in the
when I use an
in the-
equation
in
like
the
y
real
hat is equal to beta naught
right?
plus
And
beta
now,
1 x1,
as you collect more and
beta
more
1x,
data,
and when I give one
so
value
now
of
think
x,
about this.
I get only one value of y.
With the original data that
So
you
which
had,
one of these data
you had
points
some kind of a
am I
distribution.
trying to model? Okay,
And when more and
given
more
value
data
for one value of
comes
x,
in,
let us say I have
again,
10
this
values
is
of
a
y.
sample.
Okay.
Right?
Now I ask
Your
the question,
distribution might
when I
change.
give value for x, which one of these
And
data
when the
points
distribution
was I
changes,
trying to model?
your model is going to
The answer is
fail.
none of them.
Right?
Right?
And
We
that's
cannot
what
make
I'm
such a prediction.
saying,
We
essentially.
cannot make such a prediction. Okay,
Now,
in my data set,
why do
the
you
third
want
point has
to
x value is equal to something,
check
y value is equal to
beforehand?
something. The
You
20th
can
data
check
point
whether
had the
it
same x
falls in the
value,
same
but a
distribution or
different y
not.
value.
You can do that.
When I in the
Whether
model,
a new
when I
data that's
substitute
coming
this x
in, whether
value,
it falls in the
am I
original
making the prediction
distribution.
for the third point?
There is a
or for
test
the
called
25th point?
chi-square test. You
The
can do
answer
that
is I'm
very easily.
making predictions for both.
Okay, and please
Right,
go
for
check
both
for
I will
that.
get the
And
same
it's
prediction.
possible. We can do that.
So
Now,
what am I predicting then?
what is the
I'm not
purpose
predicting the
of
measured
doing that?
value.
Let us say
Therefore, what am I
when a
predicting?
new data comes
And
in,
the answer is this.
and if
That
it
is,
is
if
not
I know there are multiple y
falling
values
in the
possible,
distribution, what are you
and
going
when
to
there
do
is
with this
no
data? Are you going to say that this
extra
model
information I have,
is going to
the
spit
only
out,
reasonable prediction I have is
before
the mean
even
value.
it goes to the model? Are you
The
going
mean
to tell whoever is the end user that this data is different, so we cannot make predictions for this? Is that what you want to tell?
The mean value for one value of x.
Yeah, go ahead.
And that's what the model is.
What we want.
No.
The model is
So
not
there
prediction for
could
one
be
value of
a
x.
different model to handle it,
The prediction is
and probably route
the
this
mean
data
of
to a
the
different
all
model
possible y
to
values
make it happen for the end
for
user
that x.
to give the
That is what
to make the right.
Means you have built another model as well.
So look at the
yeah. Then you have a family of models.
notation we have.
Correct.
Sometimes,
right? So if you have
what
family of
people
models,
do,
then that exercise has already been done. Maybe that's part of this exercise.
This is sometimes
Okay.
Instead of saying
usually
split a
written
linear regression
as
model, maybe you have one pre-processing step here where you say split the data into different distributions and fit model for each one of them. When new data comes in, see which of this distribution this new data falls into, and then use the appropriate model. Right? That's the kind of approach you are looking at.
Got it. Thank you.
Yeah. Prince Dubey, you had a question.
Well, sir, not
This
a
is what
question,
usually I
but
had
a
is equal
real-time
to
implementation that
this
I
thing.
have
But what we mean is
around this, because
the
I'm
mean
having
of
a
y
multiple
for a
models
given
are
value. That's what
deployed,
we mean.
and
Okay, somebody had
the
raised
way
their hands. Please
this
go ahead and ask the question.
gets the data.
Prince Dubey, please
So
go ahead.
basically, we have a Sir, data so pipeline. I'm just and thinking that these in data what pipeline is scenarios actually I will be using it. put all the data, whatever we are getting Can I from have the one different example sources into a data that lake, and then the where I data would be using warehouses. this And that's where all the cleaning and everything which we have done earlier and the model that is deployed, that actually use, this warehouse is actually feeds the data to all the models.
In every scenario,
And
because
whatever
let
the
me take a look at this, okay?
the result set that
even
which
this
we are
grocery store
expecting,
example,
if that is within the threshold, as
let's
you
go
just
and take a look at
mentioned,
it.
are there,
For
then
a
we go
distance
ahead
of
with it.
800
Otherwise,
meters or
we
790 meters,
see
whatever
the
that is,
stats and see if our model is not doing exactly
this
what we
810
had,
meters,
what threshold we have set up.
the
Then we
measured
go
value is
back and
52.22.
retrain it and redeploy
Remember
it
my
again.
interpretation that this is just a sample from a
There is no
population.
escape from that.
So I might have had in the population, I might have had many customers who were at 810
Professor, one question,
meters
like
away,
we missed a
and
couple
who
of
had
minutes
different
to
values of
you had some
Y.
announcements. Could you please repeat if you
It's
don't
just
mind?
that the value
No,
of
the
the
announcement
sample
is that
did not bring that up here, whereas
we are
it,
not
it
getting
brought
any
that up
extra
here in this
sessions.
case,
Okay.
in this situation. But in other
What I was
situations, it did not bring that up.
was that I could
Okay.
extend the
So
sessions
in every situation,
that I
even
already
when I
had.
have only one
Okay.
value
So which is what
of
I
X
have to
and
do.
Y,
And
Sure,
I'm
brother.
going to kind
prediction
of
I'm making is
go into
the
a
mean Y value
lecture mode
I will
rather
have
than
for that
discussion
given
mode
X.
for most part of
You
the
can ask, what does it mean? I
sessions,
have
so
only
that we
one
can
value. The
cover
mean of that one
enough
value
ground.
will always be
Certainly,
the
Professor.
same value.
And
right?
as there was no
So,
extra session, what we have done is like
29
whatever was covered till
divided by
last
1 is
Sunday
29 anyway.
that we
So what do
used
you
for
mean
our
by
assignments, please consider
mean of
that.
all the measured Y
Sure.
values?
Okay, sure.
It is
Thank
not
you.
the mean of all the measured Y
Okay,
values.
now what we are going
It
to
is
do
the
is
mean
we're
of
going
all
to stop
possible
here
Y
and
values.
move on to
And
the next
in
step.
fact, as I was telling you,
What did
this
you
is
do
what the
here?
model
Make any
we were
change,
working with.
but still it
This
says,
is what we actually mean in other situations.
we are going to
people
go
usually
to
would also
the
write
next
this
big
as
problem
E
of classification. Okay, so what we'll do is we'll take a very short break. It's a change of thought process.
Okay.
So I would like to take a short break, 5 minutes break.
So this is
We'll come back.
this is the equation start with. This is
start
what we
on
mean.
this
This is what the equation that we
technique called
actually
logistic regression.
have.
This
What is E?
essentially
E
a
stands for
classification
expectation.
technique. Okay, we'll
Expected
talk about
value.
this. The
Okay.
idea is very
Expected
simple.
value for the yi.
And once we finish
When
this,
x is given. That's what
then
we're looking at.
we
Expected
will
value.
go
Okay.
back
You might have just one value of x.
linear regression and talk
In
about
the
some
data,
more ideas of
we just have only one instance of
one
xi
refining
value.
the models. Some
Okay.
techniques
But that
of
doesn't
refining
mean
the models.
that other
So,
values are not possible.
5
So
minutes
what
break,
is the expected
7:20
value
on
for
my watch
y
here. We will meet once again.
given this value for x? That is what we are talking about. Okay. So let me make this in terms of conditional probability. That notation, let me make it much better. Okay. So expected value of y conditional upon x. Oh, this is is there a vertical line here? No. Relations, no vertical line. I hate this. One thing I hate in the LibreOffice is this. Well, give me just a minute. I should be there somewhere here. It's not evaluate. Okay, you get the idea. No, it's not that. So let me go and write this. Okay. Conditional on x. Okay. So expected value for y conditional on x. Okay. Conditional on xi. This is what people say. This is what we usually say. Okay. What do you mean by multiple values of? Now, what do you mean by this mean? How? Okay. When I have only one y value, and this is where we say we come to the second assumption, which we have not mentioned at all. Okay, that is, for a single value of x, multiple values of y are possible in the data, are possible. That's a key. Are possible in the data set. Okay, if multiple values of y are possible, then these y values should be distributed in some manner. Right? Should be some distribution. And this is the second assumption we make. The various y values for a given x, for one x value, we have the set of y values possible, right? And those will fall on a normal distribution. This is the second assumption, normal distribution. Okay, and this now you can say, now if something is falling on a normal distribution, the best thing we can predict is a mean or median or mode, right? That's what we measure. That's what we predict. So what we are predicting is the mean of this normal distribution. That is what we are predicting. Okay, so let me show you what I mean. Okay, let's finish one more. The distribution of y for different x have the same variance. What does it mean? I have many x values. For each x, I have some normal distribution. And all these normal distributions look identical, except for a shift in position. That is, they have the same variance. Okay, if that is the case, then we call this data to be homoscedastic. Okay, homoscedastic. And this is another assumption we make. This is all assumptions that have been there implicitly. We did not make this assumption explicit when we started the example. Okay, but these are the assumptions that go into building the normal distribution. Okay. Yes, Chandrasekhar, go ahead.
So for your first statement of single value of x having multiple values of y, right, in the data set, it's a single linear, it's a single variate linear expression, right? And in that, simple expression, in that the only varying factor is x, because everything else is constant. So for a single value of x, even intuitively, I'm not able to understand how can you have different values of y.
See, y is equal to beta naught plus beta 1 x is the model.
Okay.
So, what I am finding is, I am finding in the data, I am finding for one value of x, I am getting multiple values of y. So,
provided, how is it possible? Is because your x is, let's say, 5, then your y will only be single number, right? Because
exactly, y will be only a single number. So what single number can I give? The only single number I can give is this expected value. Okay, so the actual model for the data, if you want to give the model, then what you have to have is something like this. Okay. Okay, so let me go. So the actual model is for a given ith point. Okay, for the ith point in my data set, the predicted value is yi hat, which is the expected value, plus some error. If you want, I can go ahead and make this as epsilon I. Some error. Okay. Now, where does this error come from? This error now, epsilon I, I'm going to say, comes from, or let's say, comes from n, or let's say, n 0, some okay, the errors in my model, okay, that comes from a normal distribution of some shift gear mean 0 and talk about, because the data point could be above the mean or below the mean. Therefore, this normal distribution has a mean 0 and some standard deviation which I do not know.
Supervised learning problem.
And I'm going to say,
called
so this
classification.
This is the actual model for every
classification.
If that is the case,
essentially means
this normal distribution does not depend upon
if you have an object. Okay, if you have an object,
which point I'm looking at,
and if this
how the errors come about,
categorized
from which distribution the error comes about, that is not dependent upon which point I'm looking at. And that is exactly what homoscedasticity is
we want to.
Okay, this sigma we
put
do not
it
know
in that
unknown
bucket
such that number. So some unknown error comes from some unknown distribution
is accurate.
Okay? But we know that the distribution is uniform for all the data points. Okay, so this is the model.
So how do we do this?
Truly,
mathematically,
this is what we should write.
This object that we want
this beta naught plus beta 1 x1
is usually
given the expected value for 1.
No, it's the same variables.
So what you're saying is that because of the
for
inbuilt error which exists, the values of y can vary because of that.
Is what defines this object.
Oh, okay. This
and the outcome variable. The outcome variable is not a continuous function like before. It's not a continuous.
Sorry, Rajan.
It's
So
not
I
a
just want to get it
continuous
understand about
variable
this the third
like
assumption,
before,
because
but
ideally
rather it's
I
a
was thinking in the earlier all
one
our
of these three
discussions.
classes.
Imagine like
So the outcome variable,
yeah,
we are
I'm
going to
also
say
getting
is one of these
in your
three,
earlier sheet also I
A,
have seen
B,
it, but
or
exactly
C,
I'm not sure
one of these
exactly
three.
which line
So
it
we
is
have
in.
to choose them.
So for example, I
Right?
have
That's what
X value,
classification
take example
problem
my
is all
salary,
about.
and then my Y value as my
Now,
spend. Okay, the money
we
I
are going to
spend.
look at a very,
So
very
normally,
simple case of this
take
problem.
example, even though I have a
Namely,
lower salary, I spend a lot.
we
But
have only two
if the
classes.
people who are having a higher
Let's
salary,
first
they
start
spend a
with the
low.
simplest case. We have
That
one
means
assumption.
it is not
Two
equaling
classes.
the assumption number 3, is it?
This kind
So
of
it's no longer the normal
problem
distribution, and
is called
No.
binary classification.
So
Binary
there
classification.
we have to look at the data.
Either
That's a different kind of an assumption. We'll come to
something is
that.
in class A or
We'll
is
come
in
to that.
class
Okay.
B.
You are. In
okay,
fact,
then it's fine.
I displayed
So
that question.
binary
I displayed that assumption just
And,
for
remember,
a minute now.
if it's binary,
I mean, that's the next assumption we are going to.
these are exclusive
Okay, then it's
classes.
fine.
No,
Then
if
I will
you-
wait. Thank
if
you.
an object,
Because
that's another
it
very
was my
important
thinking,
assumption.
so that
It's
okay,
an
how it can be,
implicit
but anyway, then we
statement
can
which
wait. Yeah.
we
Let's
don't
look at
say it
in a
explicit,
short
but
way.
it should be obvious.
Before that,
If
let me take a look at this.
An object,
I do
if
not know
one
that I
data
have this
point
here.
belongs in one class,
Let me.
I
it
saw it in
doesn't
the very
belong
first
in
where we
any
have
other
it this
class. Right?
gas,
So these are
the
mutually
bigger
exclusive classes.
gas diagram. Yeah.
And here what do we have? We have binary classes. So these are like
I want to
a
show
class and its
something
complement.
created already.
If something is in class A, it is not in class B and vice versa.
Okay, maybe this. Let me see.
Right? So it's a binary classification. And arbitrarily, we can give the number 1 to one of these classes and 0 to the other class. So two classes, 0, 1.
This is again a data which is
sometimes we call them as success and
data
failure.
that's available from the
Success
University of
means
California
1,
Irvine
failure
data set.
is 0.
So this is
usually.
some engineering
Top
data,
down, whatever,
where they have
positive,
this
negative, some
concrete
numbers,
slabs. Okay,
binary
many slabs.
terms we use to define
and
these
they have
two
measured
categories
these compressive strength.
without any
That is
meaning.
how much
No, we
pressure
don't attach any meaning
you
to
have
the
to apply
success or failure. Just
until
saying
it
that
doesn't
these are
break, or the
two
breaking point
complementary
in terms of pressure
classes.
for a concrete slab. Okay, so they have
Where do we
measured it
use
in terms of megapascals.
many different situations.
So the values are available
To say whether a flight is
and
going
for
to be
each of the
delayed or
concrete
not,
slab,
a person
they
has
had
a
these
particular
other
disease or
parameters,
not,
namely what is the density
whether a
of cement,
student
how
will
much
pass
cement was
this
used,
course or not.
how much furnace slag.
This is another
was
very
used,
important thing. Whether
how
a
much
tumor
fly
is
ash,
malignant,
what is the water content, then what is the
or
super
benign,
plasticizer,
malignant or
that's
not.
like the adhesive,
That's what is correct.
coarse aggregate, coarse
And
sand material,
whether a male
fine
is
aggregate,
spam
fine
or
sand
not,
material, and then age of the slab.
stock moves
Okay.
up or
All
down.
these things were noted for these different slabs.
So many
then
such possibilities.
we wanted to
Real
build
life,
a
you see a
model
lot of
for
different
this
things.
concrete
Quite a few of
composite
you are
strength
probably
of this
familiar with the
no?
last
composite strength of
example.
concrete slabs
and
based upon these different variables.
penultimate example.
That's what the idea is.
But these are
Now
all
for a demo,
very common problems.
I have plotted
right? Especially
the
the
compressive
medical,
strength on the y-axis
uh,
versus
examples
age,
are very common.
not age, right? A cement content. Cement.
So we again start with a
content on
simple
the
example,
x-axis.
binary classification.
Cement in terms of density, kilogram in meter cube. So that's
So
the
what is
density.
it?
Okay, density of
This
cement
example has been
in the concrete slab and its strength.
for
And
probably
as you
a
can
couple of
see,
decades now.
there is this model
Okay,
which
so
is a
the
linear
data
model
is
which goes
probably
like this.
available online.
Okay. And if
Go
you want,
check.
we can. Yeah,
The idea is
you
very
can see
simple.
what actually the model is.
No,
But
a large auto
I'm not
club.
sure whether it is a.
No, for example, AAA in the US.
No, let me
in
not
North America. So,
waste time on trying to figure out what.
So some auto club like
Oh,
that.
no.
What they do was
This some other
they wanted to
hand-drawn line.
see
Let it be. Now what I'm saying
whether
is,
they could
you see,
introduce
for a given value of x, lots of y values
a
are
supplemental
measured
health
values.
insurance plan for
Right?
their members.
And for a given for one x value, if I look at the
Okay, they want to
distribution of y
introduce
values,
whether they
this
could
might be in this kind of a
supplemental
distribution,
health
a normal
insurance
distribution.
plan.
Let's assume this is normal.
And
This is what I
before doing
get
anything,
in
no, they
terms of
want to
freehand
understand
drawing.
whether
Okay.
there will
So
be a
assume this is a
support
normal distribution.
for such a
Okay.
plan.
Now what happens
So
is,
within
every
course they are
other,
doing a
no,
market
if you
survey,
move to a different x
market
value,
research within
you
their
will
own
get
members.
essentially,
Right? So what do? They send out a
you will
questionnaire
get essentially the
and
same normal
you know,
distribution,
ask
but
them to
with
fill
a
out
slightly
in their,
different displacement, right? So it will be
membership
just slightly
number,
vertically displaced,
whatever
but the
details,
shape of it will remain the same.
and then ask
This
this
is
question.
the assumption of homoscedasticity.
One final question.
Okay, this
Whatever
is the
question
assumption.
they had
That's what I was
one
talking about
question where
when I
they
mentioned
asked,
homoscedasticity.
would you be interested
The next
in a
assumption that we
supplemental
made,
health insurance plan?
okay, we did not state it explicitly. We said I'll use this. That is,
So two
the
boxes.
target variable is linearly related to the independent variable.
and they
y is equal to beta naught plus beta 1 x. That's the equation.
And what did they do?
So that's the assumption. Okay.
They want to now ask
in certain situations
from the results
data might actually not show that. In fact, in
so
our this particular data, right, in our grocery delivery data,
got the results
we
from
saw
few members
that actually the model,
let us say 100,
could be not necessarily a straight line.
Let's say they have,
right? It could be
5 million
a
members.
polynomial like this.
First thing they are going to
like
do
this,
is
right?
not send out
I'm
these forms
just
to all the
using this.
5,000.
I'm assuming the relationship to be linear.
That's okay. Census
John Sirani, I'm not sure whether
method. No,
your question is answered by this.
Not do it.
It's answered. It's answered.
So they
Please
randomly
proceed, sir.
select
I got the point. Please proceed.
few thousand or few
We
hundred
are assuming the relationship is linear
and send
and
out
going ahead
these
and
questionnaires.
fitting this model.
And some
Right,
people
that's what we are
respond.
However,
Okay. And from this response,
that need not be the case.
what they
That
want
need
to
not be
do
the
is,
So we can
they
only
want to ask
verify
this question.
This is the first one.
If we know something
And,
about the member,
This is another very, very important
Can we predict
assumption that we make.
whether this
The
person
measurements are independent of each other.
will be interested in
What does it
the
mean?
supplemental health
So,
insurance
here
or not.
we have like what? We probably have about
That's all. That's what they want to know.
1030 measurements.
Can we
on that.
use the members'
We say,
details
oops,
and say
each one of
and
these
predict
measurements
whether they will be interested in the supplemental
is
health
independent of
insurance
each other.
or
That
not.
is the measurement
So
I made on
only
the
two
first
states.
slab
Interested,
does not
not
depend upon the
interested.
measurement of the second or third or fourth or so on.
So what did they do?
Right?
They
The
looked at
measurements are independent of each other. That's very
the
important.
data like this,
And this is very important,
So
especially when we
they
talk
looked at
about
the
some kind
age of
time
the
series.
respondents,
But here,
because
what is
they are
the
members, so they have
what is
that
the
information.
implication of this particular statement?
And
The implication
they
of this particular statement is,
plotted the
if I
age
rearrange the rows,
and
I do not
their
lose
interest.
any information.
Those
I can make
who are
the 10th row
interested,
become the 79th
they
row,
plotted
79th row
on
become
the
the
vertical
85th row,
they gave a
85th
y
row become
value
the
of
10th
1.
row. Right?
Those who are
I'm
not
not losing
interested,
anything.
they gave a y of
I do
0.
not lose any information because
On the x-axis is
they are
age.
independent of each other.
I forgot
But if
to
they are
add that,
dependent on each other, then
information
I will
here.
not be able to do
On the
that.
x-axis is
Right?
age.
Therefore, that's one important
Y-axis
thing.
is
So that means
1 means
if we want to
interested,
just test out
0
a model,
means not interested.
if you want to test out a model,
Now
we
if
can
you look at
randomly
this
pick
data,
data.
you could
No,
see
we
a
can
few very
randomly pick
interesting
few
things.
rows. Use that to test the model.
You could see few
Right?
interesting
That's a
things.
very important
What is it?
consequence of this particular
You
assumption.
see,
Yeah, go ahead. Very important
Tell.
consequence of this particular
please.
Okay.
There's no
Now
line.
let's look at all the other consequences.
There's no line.
Yeah,
First
there's no
assumption.
line.
Rajan, sorry to cut
Correct.
you.
Yeah.
Just a quick question. For the
Even if you were
assumptions
to
that you have
draw
indicated over
lines,
here, do we have graphs for each
will
of
that
them
make
that
a
would really
sense?
help us
Will that
understand
make
these
any sense?
statements?
No.
We are
Because-
going to see that.
No,
As
right?
we
It
move
will
on.
not make
Yeah,
any
but
sense.
in the PPT that you share, if you can just make the statement and the graph
Okay.
beside each other, that
What
will
is
really
the
help us
value
digest
of
this even more
0
effectively.
minus?
We are
So
going to see
draw
that. We are
line
going to see
is-
each one. Each one of
and
these
we
we
have
have
a
to
value
go
of
slightly.
0.7. What does it mean?
So
Can be either 1 or 0 because
the
this is categorical.
consequence of the first statement is that
They
we
just
can only predict the mean
arbitrarily
value
gave
for
the
y
number 1
for a given value of x, which
and
we saw
0.
already.
Doesn't
The
mean
values of y for a given value of x fall in a normal distribution.
so that's not what we want. Okay? So line will not
that
work.
means that, and
But few other
added to that,
observations
the
we can
measurements are independent of each other.
Since I
These two
told you
together
it's
tells
the
us that
x-axis age,
The errors
you could
are
clearly
distributed
see in this data.
around the value of 0. The errors
Young
sometimes can be
people
positive, errors can sometimes be negative.
seems like
Therefore,
all young
The
people
errors are distributed
are
around
not
the mean
interested
value of 0.
in
errors,
the supplemental
the
health
errors,
insurance.
the
Obviously,
residuals.
they don't care.
And this also means
young
the measurements
people,
are independent of each other. That also means
they are
the errors are
they
randomly
have this
distributed.
feeling that they are invincible.
That's the other
They
consequence.
live forever. As
Then
they are.
finally,
So they
since
don't care.
the values of y
Older
fall on a
people,
normal
senior
distribution,
citizen,
which you actually saw, it comes
everybody
from the normal distribution of the errors,
wants a supplemental health
the residuals
insurance.
fall on a normal distribution. This is actually the
Right?
assumption. I'm giving
Because
it to
they
you the other way,
know they are
but
seen
this is
and
actually the
they are
assumption. The
already
residuals
having
fall on a
quite a
normal
few
And
problems
finally,
in their
there is one other
body,
assumption, namely,
mind, emotion, whatever.
there is no outlier in the model.
So
That
they
is,
would
when
definitely.
there is an outlier,
And seems like
the outlier
people
will
of
affect the
advanced
model
ages,
disproportionately.
I do not
That's the
know whether
definition
you
of the
call
outlier
this as
when we talk
advanced
about
age.
models.
That
That
could
is,
be
if I remove a
offensive
data
to some
point,
people, but
if the model
for this
changes
data,
drastically,
we'll call it.
then that data point is an outlier.
People of advanced age.
Therefore, is it
they
possible
are
for us to
definitely
figure out
interested.
systematically which data points are outliers?
And in the intermediate ages,
So this is
where
not
we
an
have
assumption,
problem.
but this is something we will have to do.
Okay, somewhere from
Okay.
45
This is
years
something we'll
of
have to do.
age
This is a
to
part
about
of the
55 years of
diagnostic tool. If you want to
Some
state as an
people
assumption,
said,
then
yes,
we can say
we are interested.
that there is no outlier in
And
the
some people
data.
said we are
We can
not
state it
interested.
as an assumption and then go and test it. Okay.
Now
Now let's take a look
look at each one of them individually. Leads us to a different kind of a question. Yes, Chandrasekhar, please go ahead. Okay.
So
When
what is
some
the importance
people
of
say
understanding these assumptions,
yes,
sir?
Because if these
some
assumptions
people
fail,
say no,
then we don't know. We
can
actually
you,
do not
can
know
I
what
ask
we are
the
building.
question? How many people said yes?
If these assumptions we are building,
And how many people said no?
but if the assumptions don't hold true, then do we really know what we are building?
That's a very interesting question. But
So do we have to validate these assumptions upfront?
Why?
Exactly. Then we have
Because
to
the
validate
moment
these
I
assumptions.
change the
And
sample
that's where
size,
we are going.
Okay.
these numbers will change.
Yes,
Sorry,
John, go ahead.
Yes, I just want
So,
to
rather,
set the statement here. So, for example,
a more interesting
again,
question would
these
be,
assumptions are based on my data. You see, if my
what
data is not
proportion of people said yes,
That it's not a
and
the
the
assumption
remaining proportion,
is
complementary
on the data,
proportion, said
not based on the data.
right?
or
That
for
would be a
example, right now
better
we have
question to
5
ask.
assumptions. So if I
Therefore,
saw my data has some
what we want to understand is from this data,
some different
Failure of
pattern.
non-linearity. Let's say it fails the linearity assumption.
The proportion of young people
Yes. So if it is,
saying
for example,
yes,
the fourth assumption is not okay,
saying
then
yes
can I introduce the
zero.
7th assumption? Or
Okay. So what
and
we are
for
going
people
to do
of age
is we are going to
23 or
rectify
25
that failure.
to about 42, 43,
Okay,
44,
got
Let
it,
us
yeah.
say if the relationship
the
is
proportion of
the
people
linearity assumption
saying
fails,
yes
Uh-huh.
is zero.
then we are going to
Whereas
search
proportion of people
systematically for a
saying yes,
nonlinear relationship and then
people
build
of
that model.
ages 55 and above
Thank you.
is actually
Okay, that's all
1.
we are going to do.
And between 45 and
If
55,
homoscedasticity fails,
it goes from
we are
0
going to do something
and
to ensure that
it's some number
homoscedasticity
between 0 and
is
1.
valid.
And because it's proportion.
So that's the approach we are going to take.
Proportion
so if
is
any of the
a
assumptions
different,
fail,
it has a
what is the
different
remedy?
name in our field.
That's what we are going
We
to
call that probability.
Okay.
So now
we'll take a short
can
break
relate
now.
easily.
It's 8:02.
The probability that somebody of age 33
So let's take a break and let's
will
be
say
back at
yes
8:15.
is 0.
12 to 13 minutes break.
The probability
We'll be back
somebody of
when it's
age
8:15 on
47
this watch here.
will say yes, maybe 0.4. Okay. Probability somebody of age 70 will say yes is 1. Right? So we have that. So now what we can do, we have age on the x-axis and treat this as probability values. Probability is a continuous function because it can have any number between 0 and 1. Therefore, we can build a model. We can now draw a line. Now that line makes sense. But that line cannot go beyond 1 and that line cannot go below 0. Not only that, that line cannot be just a straight line because we need to have a line that looks like this. Right? We need to have a line that looks like this. So the probability that somebody will say yes is a non-linear function. It's not a straight line. Right? It's a non-linear function. And this kind of curve, as you can clearly see, looks like a distorted S. Distorted S. Right? So it's called the S curve. S curve. This is also called the psychometric function. This is also called the logistic function. That is where the name of this model comes in. Logistic regression model. So it's a logistic function. It is also called ogive. I do not know the origin of this name, ogive. This is what psychologists use, specifically people who do mathematical psychology, who come up with these crazy formulas. Those are the people who use the word ogive. Psychometric functions, econometric functions, any metric functions between two binary variables, S curve or logistic function, multiple names this has. And the mathematical form of this is the predicted probability. We are going to predict the probability, right? We are not just saying probability. So we are going to predict the probability that something has a value. Age has for age of some number, the predicted probability that this person will be in class 1, that's given by this horrible looking mathematical expression. Okay. But don't worry about it. It's actually very easy. E power some number divided by 1 plus e power some number. Okay. So it's actually quite symmetric, if you can see this. What is E? E is a very crazy number. it's something like 2.71828 data. I don't remember anything beyond that. It's like pi. Pi is a number which is like 3.14159 something, right? So it's like that. This is called an irrational number. You cannot represent it as a ratio of two integers. We cannot do that. Okay? So there are infinity of irrational numbers. We have name for few of them. One of them is pi. The other one is e. I don't remember any other irrational number that has been named. Maybe there are some, but I don't know the name. Okay. So this is e power something. What is this something? That something is a linear function of the variable. What is the variable in our case? The variable in our case is age. So e power beta naught plus beta 1 times age divided by 1 plus e power beta naught plus beta 1 times age. That's the model we have for the predicted probability that that person is in class 1. Okay. So what? There is some math equation. So what? Okay. So, okay. This has to be had. This is not just probability. It has to be predicted probability because we are building a model for the probability, right? It can be a single variable or multiple. If it's a there are many variables, then you put all of them like this here. Put all of them like this here. You already see where we are going. Regression, logistic. This is the logistic function. Here you can see some form that looks like the regression, linear regression form. Therefore, this is a logistic regression. Okay, that's what it is. Now some definitions. Okay. Yes, Suvir Bajaj, please go ahead.
Sir, is it possible to go one slide back, please? So in this slide, the formula states 1 over 1 plus e raised to negative mu. And in the next slide, okay, I'll wait for you to explain it before I ask my question.
Okay, so e power, anything power minus something. In this case, e power negative mu is the same as 1 over e power plus mu. Okay.
Got it. Thank you.
So let me do one thing. Let me do a new slide. Delete this. Go here. Copy this. Paste this here. So what happens is, okay, let me do simple. Control C, Control V. Now this becomes 1 over plus okay. This is what this is. 1. So since e power minus mu is 1 over e power mu, it becomes like this. This thing we can rewrite again, right? Yes. This thing we can read it as 1 over e power mu plus 1 over e power and no, not this. This looks so this has to be like this, right? So I cross multiply 1 plus e per mu by e per mu. Now our standard thing is this is nothing but 1 over something is the reciprocal of that something. You have to reciprocalize, right? It's a reciprocal of the reciprocal of this. So e power mu goes up. Therefore, this becomes, so this becomes this is equal to e power mu over 1 plus e power. So these two are equivalent. So this is the math involved here. Is that fine? Was that the question?
Yeah, yes, thank you.
Okay, sure. So now we go to the very basic probability question, that if the probability of being in class 1 is something, what is the probability of being in class 0? That would be 1 minus that something, right? It would be the probability of being in class 0 is 1 minus p, where p is the probability of being in class 1. Okay. So when you do that, okay, again you have to do the reverse of what we did in the previous slide. So this would become 1 plus e power something minus e power something, the whole divided by 1 plus e power something. Okay. So this becomes something like this, because there is 1 plus e minus e, therefore plus and minus cancel. So the numerator has 1, the denominator has this. Okay. So 1 plus e power something. This is what is the probability that the data is in class 0. Class 1, this is the probability. Class 0, this is the probability. Okay. This is simple math algebra again. Now, if you take the ratio of these two, P divided by Q, probability in class 1 divided by probability in class 0. Okay. To take this, what do we get? This thing divided by this thing. So the denominators gets cancelled. Therefore, we get P over 1 minus P is e power something. This form. Okay. So what is this? This is probability of success. Usually people say this way: probability of success divided by probability of failure. There's a possibility you might have heard this term, this ratio. This ratio is called odds. This ratio is called odds. Odds is probability of success divided by probability of failure. So the odds that something is in class 1 is given by this expression. Okay, we call this odds. Okay. We will start. It's very easy to go from odds each one of these assumptions. In fact, let's do that. I do not know. Yeah, go ahead. Have done that.
Yeah, I have one question on the previous slide, second assumption.
So let's do that. Okay.
So as per this, for the various values of y,
okay,
for a given x, fall in a normal distribution. So let us assume that it is forming a mean and a standard deviation. Right?
Yes.
So in that case, when I do a linear regression, I will be able to estimate the mean, but the actual value will be having an error with respect to the standard deviation. So if the original data, if it is having a higher variance, then I will not be able to achieve R square close to the 1. Is it correct?
Hold on. What do you mean by higher variance? Higher variance than what?
Okay, so with respect to the mean, if my data is having a higher, it is not converging, which means that, like, with respect to the mean, it is like I see that vertically it is spread across for the same x value.
Yes.
Now, in that case, though I do any correlation, I will ultimately be not be able to predict the value exactly, because the data itself is having a noise bill.
Yes, times 2. Exactly. Now let's take a step back and ask this question. Okay, let us assume that homoscedasticity and this normality and this linearity, independence, all these are valid. This leads to this the standard deviation of the unknown normal distribution
standard deviation of the error, which you do not know, and let's assume that's large. Okay, then what would you see in the data? You would see a straight line.
So what do I want?
Which is the model.
I want to
which is predicting the mean value
P
for the
all in
normal
the same
distribution
place.
for a given value for one value of x.
So this becomes
That's there.
yes.
And then if you look at the data
is
itself,
equal to
that would be very much scattered around that straight line.
P.
And what is the consequence of this? The consequence of this is that the sum of squared errors will be fairly large.
What do I do?
That is your R squared value will be a small number. Okay, so the assumptions could be valid. They all could be correct. But the just that R squared is small tells you that the distribution of the errors has a large standard deviation. That's the connection.
So ultimately, through these 5 assumption or constraints, we try to say that it is a IID process of a random variable, which is dependent on the dependent variable what I have calculated.
Correct.
Okay, got it.
Okay. So he used the word what is called IID. IID is a short form for independent identically distributed. Okay, so each data measure, each point in the data set is independent of each other. So that's what our final statement here is, the measurements of independent of each other.
So you see
identical,
very symmetric.
That's what homoscedasticity here means, right? Okay, so they are IID processes, correct? IID normal processes
in terms of odds,
and then that's the assumption.
In terms of P.
Now let's start checking each one.
Very similar, just the change of the sign.
So demo using empty cars data set.
Yes, which is the
I
odds
do
is
not know what I was
probability
trying
of
to
success
do here, but
divided by
empty cost data set is not a good data set for
probability
demo.
is
Model
odds over 1 plus
Let me use some other data set. Okay, let me go and
so
say wind turbine.
It's very symmetric relationship.
Wind power data set. Okay, so let's go take a look at that.
So what? So what I'm interested in is,
I'm going to close this.
So what I'm interested in is not this relationship actually, okay, but something much different.
Let me.
You see, yes, Sam Liang, please go ahead.
Today's date.
Yeah, we have used the word odds in our conversation before. So let's say if someone were to ask us, what are the odds
another fantastic
that a student completes the GGU DBA program?
From the same textbook I mentioned earlier.
What are the odds that a student completes the GGU DBA program?
So
how do I go about using this formula to answer?
This wind power windmills. Well, and what we want to do is the power generated is a DC power, right? Because it's essentially like like this thing that's rotating inside a
I have always never understood
the fans of the.
In fact,
the wings
of
the
fans in the very
are connected to a motor.
I would have said,
or actually a coil. That's essentially the basis of it, which lies inside a
complex
permanent magnet.
Because when mathematics,
the coil rotates inside this magnetic field.
Likewise, after I have produced these concepts,
if you remember
these terminologies,
I avoid
using those terms like
so a direct current is produced.
Now, what is the odd of something?
Whatever that be. So
people,
the power produced by a particular windmill depends upon how fast the motor was rotating.
But the actual meaning of
and how fast the motor was rotating depends upon the wind velocity in whatever units. This could be whatever unit it be. Okay. And
people
DC power in
which is a very technical
kilovolts or whatever. Let's not worry about the units.
I don't know if I can call it a profession.
This is the data that's given.
Okay. Professional gambling.
If you plot the data,
betting, odds there has this exact meaning. P over 1 minus P. Probability is never a number beyond 100%. But odds can go way beyond 100%. In fact, you would have seen
here's the
10 million to 1, 10,000 to 1.
So as you can clearly see, this is not linear.
No, the data is not linear. When people say odds,
the data is not
say
what I have done is I have gone ahead and drawn the linear model.
Winning this championship.
I have drawn the linear model. The linear model equation is given here. Okay,
that's what people usually say. That means they are talking about this probability. 1 over 5 is the odds they are talking about. Okay. So, so what is the linear model? The linear model is 0.
So that's the only meaning of the words odds. Beta 1 is 0.2411
I know.
x, where x is the wind velocity and f of x is the power produced. Okay. Now, and you can see the errors. So using this equation, because using this equation, you can see here, using this equation, I can go, okay, here is some example. I can do one more, some more explanation of what is 1309. Odds is defined as, and I could do this for probability of success things over probability of failure, and ensure the, when everything is in class 4 decimal places, when P is 1, then odds is infinity. So here's the Y predicted. Odds infinity. Okay, predicted. Everything is there. DC current and measured is here. And here are the errors. When probability of success is 0, what did we say? We said that it's very close to 0. It's undefined. It's actually, if it is linearity, it's close to minus infinity. Then, but it's undefined. There is no pattern in the residuals. Also, we can say it tends to minus infinity. There is no patterns in the residuals. But if it is linear, 0 by 1, and randomly any number is undefined. If randomly divided linear, divide 0, then there will be no patterns in any number of residuals in errors. So I plotted the errors here. When odds is, when probability is 0.5, halfway errors. That's what I have. This is a very interesting situation. Okay, so predicted odds is 1 on the x-axis, and the errors on the y-axis. That's what I have plotted. Okay. Now, so you see, what does it? Here is the 0 line. The residual should be randomly distributed along 0 line. When, as you can see, odds that's not the power something. Right? If you look at the errors, there's a pattern. The errors in themselves seem to follow a parabolic pattern. That is the case. If you take the logarithm of odds, a pattern like this, E and log like this, or definitely like tells you functions. One of two things. Okay, what is this? If you take the errors, logarithm of this or randomly distributed, logarithm of that assumption fails, then you get just and slash r. The errors are, sorry, the relationship between y and x is linear. That will be equal to that assumption fails. Exponent. When the linear assumption fails, you will see a pattern in the errors. If you look at this equation, okay, so this is the easy diagnostics. Just plot the errors. What is the x-axis? X-axis is the y hat value, predicted value, right? You don't plot x or y. Why? That is why, because the moment we go to multiple linear regression where we have more than one dependent variable, one independent variable, we do not know which x or x we have to plot. We are going to fit a model for. We have only one predicted value. We are going to fit a model for. What we do is use the predicted value. What do we mean? We have found the relationship between the predicted value. We are going and the independent variable. To this logarithm. So you take the predicted value on the x-axis and plot the errors that we get on the y-axis. If you find any pattern, then the linearity assumption fails. Okay. That's what we are. If the linearity assumption fails, what should we do? What is that? Something we have to rectify that. That's something we are going to do. In this case, if you look in this particular data set, it's very obvious that the data is not linear. Or what is happening? 80% pass and 20% failure. Then the odds is 4. This means student is 4 times more likely to pass than fail. So we exactly John said that the data. So we are very confident we have likely 4 times likely to pass linear. Okay? Because that's occurred naturally in the data. Therefore, if I were to define a new variable, let's see. Okay, new variable I'm going to define in any model which is a non-linear function of parameters, which is a non-linear function means finding the and use this new variable of this in the linear form in my linear regression. Then I have solved the problem. Is optimized, right? In linear for regression, example, I will not even call some. What I have done is I have created a new variable here. What is the new variable? You can see function is optimized. I did this 1 over square root of some cost function is minimized. You can see the cost is minimized. So I'm using 1 over square root of x. Okay. What so this is a non-linear function of the original x. Y hat is equal to beta naught beta 1 so on. And here's the y value. And then we have the cost function. That's the sum of squared errors. Right? Now what I do, I do a linear regression for these two variables, beta naught beta 1 etc. Y and x, where y hat is logarithm of odds. Look at this in this diagram. Can we use sum of squared errors? We cannot. I have plotted. Why? Because we have no measured values of odds. We have no measured values of logarithm of odds. We are working in the probability world. X nu along the x-axis. We are not working in the actual and y along the y-axis. There is no measurement. That's what I have plotted. Except categorization. And now you see the most. It falls on a straight line. We could use this. How of course, because of the way I have categorized, created the non-linearity. Initially, it was both were positive. That is the correlation of positive. Now, with the new variable and y,
put it in
the
class
correlation
0.
is negative, doesn't matter.
Am I
But now you see the
all
relationship
my
is linear.
ones
And as you can
also
see,
in class 1?
as you can,
But
give me
this is not
just
about
one minute,
that.
okay?
Right? This is about probability. We do not know that. What to do with this?
No,
So
as you
we
can see, the
go
R squared
to
has now
a
drastically
new
improved.
concept called
Okay, that's okay.
likelihood
How about the errors? How about the errors? Have they become now
we go to something
patternless?
called a likelihood.
So let's take a look at the errors.
This is a kind of very
Here's the
difficult,
errors.
I mean, might be a slightly confusing
Take this, move this away, and let me do this
idea. But think of it this way.
numbers.
Okay. So the idea is this.
So you see the trend line. Trend line is
Let's say
has a 0,
we
0.
have
Okay, that's
a distribution
around 0, and
okay, a
the errors,
distribution.
unlike before,
And
earlier
then
how was
from
it?
the
It was
distribution,
beautiful.
we would say, okay,
Inverted parabola.
what is the probability
Now after the
of getting this
new
value
definition of the new variable,
that
we
we
got
can get from the distribution?
fairly, so it seems fairly random. Fairly random.
Now look at the
And
other
centered
way.
around 0. Okay, there is no pattern
I
that is
have
discernible here. Okay,
the
so we have
value,
solved this problem of
the
failure of
probability
nonlinearity
of getting this
by
value
defining a new
is some
variable
number.
based upon an old variable.
Okay.
And this technique is
So
called
what
data
distribution do I
transformation.
have?
This technique is called data transformation. Nimesh, John Sirani, and then Mohammed
That's the
Niaz.
kind
Please
of
go ahead.
question we ask. Okay.
Yes,
So what is
Professor
the
Rajan, I
likelihood
tried to, I could not understand
that
how
this
you
data might have
moved
come
from
from
the x value,
some
the x new value to 1 divided by square root
That's the
of
kind of
x.
question people
Like,
ask
what
when
is the
people
basis
talk
for
about
How I
that?
moved from
likelihood
this
function. Yes, Suvir, please
to
go
this. That's
Yeah,
your
yeah,
question.
yeah.
So just
Huh?
to create
I haven't
That is
told you that.
some
I just
continuity,
done this.
is the likelihood
Right?
function
I did
still
not tell
under
you
the
why I
same
did that.
theme of
Why
binary?
1 over
Are we
square
still
root?
under the same
Why not
theme by
something
itself?
else?
We're not.
Yeah.
Right? I have not told you that.
Likelihood
We'll come to the
function
next.
Rajan, this is my question actually. So why we are using the square
Okay.
root? Because if I
Uh,
take a normal student's record, I would have
in
even
this
used something
case,
different. So
it's
that's my second
more
question.
like
So, yeah, please proceed.
Yes. So we'll
yeah,
come to that in a
it's
short way.
continuous function.
Mohammed Niaz.
Okay. So
Yeah,
it's
Professor.
not
So
binary.
we were in our assumptions, we
But what we
were
are going to
taking
do
that
this is the
there is a
reasoning we are
linear
doing.
relation
This is the
between
reasoning we are
the
doing.
dependent variable and the target variable.
At the end of the
But
day,
now in this process, like in this step,
okay,
what we have done is
when
effectively
we
we
have a
understood that
model
it is not
and the
linear, it
model
has some
gives you some
non-linearity,
probability,
and we are manually
for
assisting
given
in
age, for
plugging in
age
the
35, it gives some
non-linear
probability.
functionality. Is it correct?
Exactly. Okay, let's say it
Exactly.
gives a probability of
But then
0.89.
finding this would
Very
be
close to 1.
tedious, right? Especially when it
But actually,
becomes a
your data
multi-variable
is 0.
linear
Yes,
regression.
your
Yes.
your
Very true.
actual
Very true.
probability is 0.
Very true.
But let's say
If we
it
have
gives me
multiple independent variables,
Hmm.
or
the linear
that's
non-linearity
another
effect
case
of one
where
variable
for
Hmm.
33,
if it is not too
it
big,
gives a value
Hmm.
for age
okay,
33.
might be overcome
It gives a
by
probability of
by the
let us say
randomness in other variables.
0.05.
Yeah, if there is an
Very close
interaction
to
between them, then it will be tough to.
whatever.
That will be difficult. Yes.
So
Yeah.
now
All those things are
what
there.
we want
Yes.
to do is
True.
we want to
Now-
create a function.
now we'll come
we
to the
want
question,
to see that in the
What kind
ideal
of transformation
when you have
happens?
optimized the function,
Okay. And as we know,
okay,
for linear function
every
is only one function. Between two variables,
data point
there is only one linear function.
that is in.
But if we
class
talk about
0,
nonlinear functions, there are infinity of
we
them.
should get a
So which one should we
probability
use?
value close
that
to
is where
0.
Our Tukey, okay,
And
Tukey was a statistician. In fact,
the
you would see Tukey's
complementary
name.
probability
If you do mathematical
to
statistics,
be close to
you would
1.
see Tukey's name in
Likewise,
throughout
and
applied statistics.
and for every
This
point,
is
very,
one,
very
that is
one
in
of the
class
scientists who
1,
invented fast Fourier transform, right?
you
yes,
should get
Cooley and Tukey.
a
exactly.
probability
Same
value,
person.
predicted probability value.
Okay. So
close
this
to
this Tukey has a lot of contribution in statistics and mathematics, and he came up
And
with
its
a very
complementary
simple
probability
idea.
should be close to 0.
Okay, I'm going to go. I should have rearranged the slides. Let me do
Right.
one thing.
When you talk about probability, and we started with the assumptions, look at all the assumptions for logistic regression. It's still the same as the assumptions for
Tukey came
linear
up with two
regression. What
ideas.
is it?
Namely,
They
one
come
is
from
called the
normal
quadrant
distribution,
approach, and then
the
ladder
homoscedasticity
approach.
is there.
Okay.
The
So what he says is,
measurements are independent,
consider a circle
and that's a very important thing.
and split it into
Characteristic.
4 parts.
The measurements are independent.
Split into 4 parts using orthogonal
Then
axis.
The
So
first
you will have
measurement,
one part,
if a data
one sector
point
would
is
look
in
like
class
this, the
0,
other sector would look like this,
its
like this.
predicted probability is also class
This
0,
is how
and
a circle would look like when they are
its
split into 4
the
parts.
complementary probability
Now
is
what you
is
says
1,
is, see
and for the next
which
point,
sector
and we
your
get all
nonlinear
these
function
funds.
resembles.
And for
Okay.
independent
In our
measurements,
case,
independent values,
in our case,
translates
the
in probability
relationship
to be
resembles
multiplications.
this blue line here. And that is what this is called the second quadrant. We always start from a given top right, point that first, and then go for a anti-clockwise. Any given so first quadrant, second quadrant, third quadrant, fourth quadrant. Right? I have so our wind power generation data probability y looks similar to the second quadrant, and okay, that's the complementary probability to be 1 minus y. Here I attributed some algorithms for each and quadrant. This is the case for every how point. Did you do that? There is no need to remember this what kind of algorithm. Predicted probability y. The idea is can be 0. Okay. If we let's say all these things I want to make this or one of these, let's say I want to make this in which case all this curve with the second quadrant look like a of course straight line. We are going to get so what should we do? Close to 0, pull it because we are along so the y-axis. If you pull it along the y-axis, 0. Okay, if I pull it along the y-axis, so for each point, since we are doing this thing would go up for each point like a straight line. That point's class value. Okay. Think of it like you are pulling it like actual. It's glass curved like this, becomes the exponent, and then you're pulling it like yes. Go ahead. So now we'll get like a straight line. That's one possibility.
So is it possible to explain the like use case of this function prior to going into formulation? Why would we use this in practical terms?
Smash them along the x-axis. Essentially, then it look like a straight line. What we want to do, pull along y and smash along x. It's not really about the formulation. Look at the look at the formulation. Think of it like a simple graph point. Now simple plot. We are in the first quadrant, use sum of squared errors like x what we used in increases from the origin linear regression. X increases to the right. Y because we also increases to the right in the errors. Therefore, you want to make you want to in this quadrant in probability you want to what can we do? Pull along the x-axis, the predicted along the y-axis. That is, we want to be stretch the values of x to or the actual values of y or both. When the model has stretched the values of x. If instead of using x, you have got the go for x squared. The predicted probability. So when x is 2, x squared becomes 4. The stretch. When x is 3, actual probability. X squared becomes 9. If it's x cubed, right? If x is 3, that is x cubed becomes 27 by this horrible looking, right? So you stretch. So that is called this symbol ladder here. That's called upward ladder. Increase the range of values. It's a product over which the variable will vary. Just think of this by doing some nonlinear class. All this is saying is likewise for y also you could do at data points. Similarly, y squared, y cubed, actual value. Okay. On the other hand, if you go to the second quadrant, the predicted from the origin should also be y increases. So you do the upward ladder, up ladder on y. But now x decreases. Remember, x decreases. Y decreases. Numbers negative values and more and more negative values. That means decreasing. Change them into. Therefore, we should do down ladder summation of numbers. If the curve looks like the second quadrant, and how do it download products can be changed. Therefore, I went for 1 over square root of x instead of going for minus 1 over square root. I just went for 1 over square root of x. Okay, why? If you do this, and if you look at 1 over something, this is again square root itself is going to very interesting. Right? If the value is 4, I take square root, it becomes less. You could see. So that's one thing. And 1 over square is the actual class. Okay. I'm reducing it's either 0 the value or it's 1, but 1 over that will increase it. So the coefficients are it will actually reduce it again. 0. So that's the kind of logic used. So use an up ladder. Then whatever is in this logarithm, the quadrant is such that the values are positive. Do a down ladder if the values are negative. So now, in the second quadrant function and the third quadrant function, we will use is what is called down ladder on x. Concave. In the first quadrant and the fourth quadrant, we will use up ladder on x. What is a concave function? First quadrant and the second quadrant, we will use up ladder on y. In the third and the fourth quadrant, we will use down ladder on y. Okay? That's the idea he gave me. Go ahead. And second idea. So that's the up ladder and down ladder. That's the up ladder and down ladder.
One thing.
What are the up ladders?
Most of the time, the likelihood functions I have seen,
so on and so forth.
Generally we use when the data, when the sample or the data that I have, it follows the normal distribution, right?
Yes. Now,
but can I apply this like this function if my data is not normal?
Okay. What if if you work with monitor technology, not monitors. The reason is like your likelihood laptop monitors does not assume anything about the monitor is made up of pixels, right? If you have a reading glass, and you go close to it, you also go close to it and look at your likelihood function. You could actually see through this, or if you have a magnifying glass, take a look at the magnifying glass and look at the monitor.
Okay, perfect.
It's not like a paper. No, you would see. And what we want to do is usually we do. If you have a high power because reaching the magnifying glass, in fact, you would see mathematically 3 dots, reaching the maximum, red, green, and blue. So what we do is take the negative of that. Okay. Now, instead of inverted U, how much light comes from each one of these? How do we do that? What do you call it? The combination of one red, one blue, one green. So this one pixel equation is how much light comes from this pixel? That's determined by the amount of voltage given to that pixel. Negative log likelihood function. And if you look at the light, we want to minimize the voltage. Negative log likelihood. It's a nonlinear function. And this is a very easy problem. Light, that's called very easy illumination or luminance. Why is it a very easy problem? Luminance is usually it's a U, something like voltage to the power. If it's a U, 2.2, you always know that there is a minimum value. Now how do we get that? There is only one minimum. We don't have that. In a U, there is only 2.2. Why not look for 2.3? Not multiple minimum. 2.27, 2.19. So this is very powerful, right? So all these crazy things are possible we can use. So what? Because we guarantee this one and only one. Not only do we want to have good transformations to remove the nonlinearity, we start with the star. We want to start with. We also now explain to others what do we do is, and while start with some mathematical values of beta naught, beta 1, beta 2 would be useful in getting highly accurate results. Calculate the logarithm of odds. If your tolerance for error is high, from the logarithm of odds, calculate the probability. So, because logarithm of odds first, we say restrict to very small integer powers only. What is it? Once you know the probability cubed, calculate the negative log, that is reciprocal of the squared, reciprocal of the cube value. If none of these what do you do? Look for go and change the values of the parameters. Some kind of a log transformation. So change the values of parameters. That is all we will do. How do we change? So use a step size. What we are not going to try all the kinds of hyperparameter. The learning rate. We are going to try fix only the non-linearities, that is like square root of cube, increase the values or 1 over x squared, 1 over x squared, 1 over x. You use the gradient descent log x technique. Log x is called. I have not told you what that is, but there is a most non-linear function you can think of. Which is or the inverse of it is the exponential. We'll talk about this maybe later in this course, or definitely this is what next course we will. In fact, if you want something like 2.2, so what do you do? Change the values of the parameters. Would be like then 10. That will be 22 by 10. You would be 11 by 5. Right? 2.2. You would calculate, which is like 11 by 5 logarithm of odds. So if you want something like that, from the logarithm of odds, you could do odds. From the odds, calculate the probability transformation. From the probability, calculate y power 5 negative of the log likelihood function. See whether it has decreased. That will be the same as y is equal to x power 11 by 5. Repeat the process. Some weird numbers like that. And it is possible. You can mathematically reaches a minimum value. But we say, it reaches the minimum value? You know, because so if at some point it starts to increase, your data is fairly non-linear, and none of these simple non-linear transformations, stop that, nor log, go back one step and use that. Is able to tame whatever parameter values. Then what I would suggest are there is okay, go for purely mathematical transformations. Hunt for a good. So that's what we will do. Transformation in terms of. But another probably an easier method would be see whether you have estimating the parameters is no different. Variables, same thing like and before, perhaps they would probably use the gradient tame this instead of sum of squared errors. We are just using negative of that. So
like no trigonometric relations were suggested here.
So here is an example. Here is the example. Trigonometric relations are not suggested basically because I did trigonometric relations are useful for when you see a repeated behavior, screenshot from repetitive behavior for this data, right? So that's why I did this. Don't have this in R. Sorry. In so Python. What do we do? So something like this. And here is the linearity assumption failed for screenshot of that. Therefore, we define a new variable. You can see now some code which is a non-linear transform of the original. Look at the independent variable. Now use this new variable in the linear form of the model. Go fit this model, and whenever a new data comes in, constant transform that data into new variable and put in this model to make prediction. So what do we have? The model is, and this is minus 20.41. We fix 0.4 linearity 3 times. This usually also that's what the model is. What is the model for? Independence. The model is for the logarithm of odds. That not only person will say it also fixes the failure of. What is independence? That's what we talked about earlier, right? The errors are randomly distributed around the logistic mean error line. Gives you some the mean error line is p-value flat at 0. You can immediately guess what is error distribution itself has mean 0 and some likelihood ratio, right? So if your errors on the other hand has pattern, the moment you think about this for sinusoidal function, immediately think of Muhammad. Here it is something in some linear regression.
We use
Here,
the ratio.
this looks like random, but if you look closely, it is not random. This is also cyclical.
Remember, they have
Down, up, down.
That was a ratio of
down, up. That's
two
a pattern here.
variances. Regression.
So when we have
over
something like this,
residual.
this means likewise here we have two
Errors
logistic
are
two
not
log
log
likelihood function values. When there's
What are the two log likelihood
then
function
the errors
values?
are not independent.
One log likelihood
Error
function
at one
value
point, you can use
using
that value based upon the errors
the
at
model.
earlier points or subsequent points.
With the model.
So these are not.
What is the value we get?
On the other hand,
Log likelihood.
we want something like this. Then there is
And
one.
how do we
model
fix
with
this? There is one log likelihood
independent
function value
dependent
without the
errors.
model.
Data transformation.
No,
you
when
use
age is 0.
QK's idea.
Without the
Usually that
model.
will help fix
What
the
is that we get?
failure of
So take the
independence of
ratio
errors
of these
assumption.
two.
Okay,
And
then
that will be
another very important
do this
and then assumption is the
calculate the
homoscedasticity.
p-value.
You see the
Homoscedasticity
p-value is
practically
when,
0.
let's take a look
For
at
the
our
model,
which is good wind power data. Right?
Then you look at
Let's
the
look at the errors. Originally
parameter
the errors were like
space.
this.
All the
With
p-values
the
are
nonlinear
less than 0.
transformation, and our errors
Less than
came out to
0.05
be something like
0.
this.
Therefore, this
So there
model
seems
is
to be now
agreeable, workable,
independence of
usable.
errors. But if you look at the range,
What is the equation?
over which the errors
The
vary,
equation is
okay,
logarithm of
it
odds.
seems to
That's
go
what we are
down
modeling
for
That's what the parameters
higher
talk
and higher
about, right?
values of
Logarithm of odds is
predicted
equal
Y.
to minus 20.41
Here,
plus 0.425.
the range of values over which the errors vary seems to be small compared to this region.
What I want to know is what is the
That means
class?
the
Will a
standard
person
deviation
of
of the normal
age
distribution in this new variable
55 or 51
doesn't seem to be a constant.
or 50, let us say.
So
A
this is a
person age
failure
50.
of homoscedasticity.
Will this person
This
say
is a
yes
failure of
or
homoscedasticity.
no to this supplemental health insurance? That's what
This
I
is
want.
really a failure of homoscedasticity? Maybe.
How do I do
Maybe
that?
it's a small
All I can say
amount
is
of
with this model, all I
variable.
can
If you look
say is
here, no, it
what
seems to
is
be
the
lower and
probability
seems to be constant throughout.
that
Only
this
the top
person
one
will say
there seems
yes?
to be a reduction here. Okay.
Right? Why?
So
Because
if you are
from
okay with
logarithm of
this,
odds,
even visually,
I
if you are
substitute
okay with
the
this, then
age
go ahead and
here.
start using it.
So in a substitute
But if you are still not happy, you want a
50
truly
times
homoscedastic
0.4,
behavior,
so that
then
will
what
be
you should do,
0.2 something.
perhaps this non-linearity is
Sorry,
not
20
is
point
not
something.
sufficient.
So that will be
Go look for a different
some
kind of
number
non-linearity.
here.
That's all.
So that will
Let's
be
search for a
the
different non-linearity.
logarithm of
So
odds.
some kind of non-linearity will be able to
From
fix
logarithm of odds, calculate odds.
homoscedasticity. Yeah.
From odds, calculate probability.
So here are
and that
two
probability
examples of
that's what I can do
failures
with
of the
this.
homoscedasticity assumptions. Right? Okay, what is it?
So here I substitute.
Y predicted on the x-axis.
So
The
logarithm of odds
residuals on the
becomes
y-axis. By the way,
0.88
plots like this, where you have predicted y on the x-axis and the residuals,
Therefore, odds becomes
predicted y on the x-axis
2.4281.
and the residuals on the y-axis. These kinds
Which
of
is e
plots are called
logarithm of odds.
residual plots.
Now, since I know odds is equal
Residual
to p
plots, very
over
simple.
1 minus p.
So in the residual
Therefore, I can
plots,
calculate
if you see this
P.
kind of a
P is equal
behavior,
to
where
odds over 1
you
plus
see
odds.
the residuals, the
Right?
range of
Odds over
values
1 plus
over
odds,
which the
when you do
residuals vary
Probability that
depends
this
upon the y
person
value. Y
will say
predicted
yes
value
is
the predicted y value.
0.71.
Then your homoscedasticity assumption fails.
Okay.
Whereas on the other hand,
This
if
is
you
not
have
the question
something
I
like this,
asked.
the
The
bottom one,
question I wanted to answer
then
is
you
ask
have
is
the adherence of
whether this person is
homoscedasticity
going to say yes or no.
So residual plots are
Okay.
sufficient usually
But I'm giving you
to
the answer.
look at
The
homoscedasticity.
probability that this
failure
person
or
will say yes
success.
is 0.71.
But of course,
What can we do now?
The statisticians, there is a saying
Now,
in that statistics. Okay,
We have
you
to look at
probably
this
are familiar with it.
probability
Okay,
and see
if
is this
you
probability
data
high?
enough,
That's the question we
okay,
ask.
it will start
Is this
giving you the
probability
answers
high?
you want.
If this probability is
That's a
high,
saying like that.
I will put this person
There
in
is some truth to the
class 1.
statement. So I am
Why? Because we
very
are
cautious
calculating the
of
probability
overdoing
for
any
class
analysis.
1.
That's my approach.
The upper
I
class,
usually
not the lower class.
leave it
Right?
for the human judgment.
So we are calculating
Let there be errors in the data.
the
Let there be
probability
some
to be in class 1.
that's
That's
what
what
I
I
am
am
calculating.
calculating. If this
Let's
probability
take
happens to
decisions
be high,
based upon the need
then I will
and the
put this
problem
person in
and our
class 1.
tolerance. That's the usual approach.
If it is not
But
high,
anyway, so
I'll put this person
there are other ways
person
of
in
testing
class
for
0.
homoscedasticity. One
So what is high? What
way
is not?
that people do this is
There
a
is
small
something we have to
variation of
decide.
the
We have to
residual
decide.
plot.
The
Okay?
model does
What
not.
people do is the residuals, okay, residuals.
So
can
we
be
have to set
positive
a threshold
or negative. Okay,
for this.
but what people wanted to do was let's make it all
So you see,
positive.
this logistic
Okay,
regression,
in
in
fact,
fact,
positive.
in all
So
classification
what
problems,
this
this
people
is
have done is looked at the
a two-stage
standardized residuals.
process.
The residuals
Two-step
themselves
process.
vary in some values.
You
some minus
build a
values, plus
model
values.
for something. In
Now
this case,
find the
we build a
standard
model
score for each of the residual values.
probability.
Take the absolute value. Take only the magnetic cases we are going to do. Okay, we build that and then take the square root of it. I do not know why we have to do the square root. And then set the square root of the standard residual square. Second state, square root of the square root of the z square. Probably is greater than some number. Put it in class 1. But people do this. If not, put it in class 0. And then you look at how this is what we do. So we have to square root of the standardized residuals are. In this case, no, the x-axis is the predicted y, no fitted value. And if you see, if you find something like this, then in an unbiased, if your homoscedastic assumption fails. See here, you would say halfway in this region, halfway through, except for these points here, these points. No, you also have that could be a good 6 threshold for 11. Some numbers are classifying. So let's see. We'll understand what these numbers are. If you forget the logical, seems like in this region. So in fact, in this entire region, number, the homoscedasticity is closer to 1 is valid. Than this region, it fails. Therefore, that's what this trend line also tells you. Yes, that's what we are here. It's fairly flat. We are going to say that this person will say yes to that. Okay. So maybe these 2 points are outliers. These points are definitely outliers. Okay. These points are this is how outliers. We do. So maybe that's the case. Here is another example where homoscedasticity fails. Much better. Price of Big Mac graph. This is drawn with the data. I shouldn't have put this graph here, but I will leave it as a. Here is the bedtime reading. You can go look for something called threshold on the probability. Big Mac economics. So if the probability is what these people, a couple of statistician academics, what they did in this late 90s, I will put them as that in class 1. They wanted below this dash line. Find how good can we use Big Mac, price of Big Mac. But you see, as an indicator, I can do it this way of how good the economy is of a particular all country. Ages. Okay. Big Mac is available in about 48 years, 20 countries or so right now. They all have. And our probability value greater than available in 140 countries or so. So they now prices of instead of setting the probability threshold on and then probability, I set the threshold on this with the GDP, variable itself, per capita GDP, all other indicators you can think of. I set the threshold on the variable, and then they built a model for you see what could be the price of Big Mac in a classification boundary. It's GDP, it's whatever in the feature space, percentage of export as the feature space, percentage of export as a percent of GDP. So anything to currency, I will classify with respect to dollar or whatever. Anything to the left, multiple indicators, I will classify, and then build a model for the price of Big Mac in that. So we define a boundary, and in that using that model, in the feature space. When you look at the residual plot, now you get something like this. If I change, seems like, for example, independence of measurement psychology, valid, for example, in psychometrics, seems like many places linearity assumption is also valid because people never accept 0.5, but as the homoscedasticity threshold for fails. Why? Fails. Here, I can close my eyes, range of values, or keep your eyes open, do a coin toss, for which, and whenever you get residuals very small, put in class 1. In this, whenever you get 10, put in very high, doesn't care about, and here it's probably coming down, right? Okay. Yes, go ahead. The probability that you will get,
can I say that
success is 50%.
Lower the price countries, it is more accurate.
Yeah, so that's
the readings are more accurate for lower price.
Therefore,
whereas if you have higher price countries, it's more unpredictable. They're more spread.
In random classification, you get 50% success. Okay. And why does it happen? It happens because we don't want remember that standard so that normal distribution I was talking about for different values of x higher and how they have the same standard deviation. The same standard deviation. If you want to give a higher probability fails here. What could be a higher? That's why it's accurate here. In this region, halfway between 0.5 and the standard deviation of these values varies here, which is so that's the failure of classify. Right. How do we fix this? Right. Data transformation. Okay, that's what in this case, Tukey's quadrant is not going to help you because you might not find your boundary shift non-linearity. You may not find non-linearity, but you will have to try different transformations, right, and see how we can get rid of this. Your boundary shifts in new position. Okay. So we are three very important assumptions: non-linearity, independence of measurements, homoscedasticity. Another major assumption is what is called the probability threshold we want. Okay, again, very poor animation. So please excuse me on this. Let's take a look at this. Normality of assumptions. What is this normality of assumptions? Remember, we said that all the y values will fall on a normal distribution. Why? Because our model, remember we said yi is equal to beta naught plus beta 1x plus some error. And that error is normally distributed. What is that error? That is a residual error. So we have to see whether the residuals fall on a normal distribution. How do we do that? We do that using the idea of quantiles. Remember, we studied quantiles. So we'll understand what this is once again. What is a quantile? A quantile is subdividing the entire range of values, the entire data set, into some subregions such that each subregion contains the same proportion of data. Okay, same proportion of data. So if I divide into 4 quantiles, each subregion contains 25% of data. The range could be different, but each subrange contains the same proportion of data. If I divide it into 10 groups, each subgroup will contain 10% of the data. Okay, remember this. That's the idea of quantile. Now let me ask you one question. Let us say I have n data points. Okay, so I sorted them. N residuals. So I'm looking at the residuals. Let us say I have the n residuals. Okay, I have sorted them. Now, if I split this data set into n quantiles, how many data points will I find in each subgroup? I divide this entire data set. Yeah, please go ahead.
Yeah, could you please repeat this question?
Let us say I have n data points. Okay. Now I divide it into n subgroups. That is n quantiles. How many data points will be there in each quantile? Now,
One.
And there will be one data point. That is the idea we are going to use. Okay. So now, what are we going to do? We are making the assumption that the data is normally distributed. Correct? So what we are going to do is normal distribution. We do not know what the standard deviation is. So what we are going to do is convert this data into standard scores. For standard scores, we know the standard deviation is 1, the mean is 0. Okay. Now you got this. You converted this into standard scores. Now you know how many data points you have. N data points. Now look at the standard normal distribution. And divide it into n subgroups such that each subgroup will have the same probability. What is the probability in a standard normal distribution? That's the area under the curve within that. So let me show that. So if you have the normal distribution like this, if I have n data points, okay, and if I divide the entire normal, in this case I'm taking 11 data points. Okay, my n is 11. So I divide the entire standard normal distribution into 11 quantiles. What does it mean? The area under the curve between the leftmost point and this first line is something. That is the same area between this and this yellow line and the curve. That is the probability of finding a point in any of these regions is the same. Probability proportion, same thing, right? So probability of finding a point in any of these regions, they are the same. That's what it means. Now here's the catch. Say it again.
1 over n.
1 over n, exactly. That will be 1 over n, correct. That will be 1 over n. Now, the question is, if my data points are normally distributed, I would expect to find 1 point exactly somewhere in this region, in each one of these regions. Correct? Somewhere within each one of these regions. So that's why I have plotted this point, 1 point slightly to the, let me make it more egregious. Okay. Maybe this might be slightly towards the edge of some region, but they're still within those regions. Right? So within each region, I would expect to find 1 point. Okay. So what I do is I take the center value for each of these regions. I plot that along x-axis, and I plot the standard score for these points. What are the values of these points? That I plot along the y-axis. If the data is normally distributed, I should see these data points lying on a diagonal, approximately. I should be expecting to see these points lying on the diagonal. Okay. On the other hand, if the data is not normally distributed, okay, so there might be some regions which do not have any, some of these quantiles might not have any data point. Some of these quantiles might have more than 1 data point. Right? That's possible. The red ones. The blue ones are fairly normally distributed, the red ones are not. Okay. Therefore, if I draw, I don't know what this is again, another very egregious example of non-normal distribution, the black points. Right? So if the residuals or if the data points are normally distributed, in our case, these are the residuals. This is the 45-degree line, no? So 45-degree diagonal line, okay? And these are the points on this. This is the kind of plot I would find. This is called the QQ plot, theoretical, experimental. Theoretical Q, experimental Q. You know, I'll find like this. Always the edge points will be very different. Why? Remember, in our normal distribution, the edge of the normal distribution is minus infinity. Okay. Therefore, where is the center? Center is also somewhere near minus infinity because infinity has no definition, right? So you would expect the last point, the edge points, to be fairly deviated from the diagonal line. But every other point, you would expect them to lie close to the diagonal line. For a good QQ, good normally distributed data. For a bad data, that is the data that is not normally distributed, you would find lots of points that are far away from the 45-degree line. Not just the edge points, quite a few others, fairly away from the 45-degree line. This QQ plot is one of the most powerful techniques to determine what is called the normality of a data. Okay, when you have a data, you can check for its normality using QQ plot. There are quite a few other tests. People who talk about something called Kolmogorov-Smirnov test. Then there is some Fisk test and quite a few other tests. Okay. I do not give too much importance to them. I use them only if a reviewer says you have to do this. When I publish, and when the reviewer says you have to use this, only then I use that. For all practical purposes, I do QQ plot and see whether the data looks like what is on the left or on the right, and depending upon what I find, I make my judgment call. Okay, most naturally occurring data fall on a distribution that look like normal, but may not be perfectly normal. Okay, so you might find slight deviations from what you see on the left hand side, but not egregious like what you see on the right hand side. Somewhere in between. That's what we usually find in real data. When that is the case, then I make my judgment call and you assume that things are normally distributed. In fact, one of my advisors, he's not necessarily he's an advisor. He was my colleague, but at least one generation senior to me. I have a lot of respect for this person, and he has his master's degree in operations research. One of the greatest teachers I have ever seen in my life. And he always says, I won't even look at this. I will look at the distribution itself, just plot the histogram and see if the histogram is fairly normal to look at. And that is sufficient in most cases. Okay, that is sufficient in most cases because the statistical tests for normality, they all make few other assumptions and they are very strict and they are actually quite powerless. That's what you say. So in a summary, as long as your QQ plot looks reasonable, you could go ahead and say assumption of normality is valid and move ahead. Okay. So when that is the case, what do you have? There is only one more thing to worry about. What is that one more thing? Right now it's the time we have to worry about the outliers. Okay. If you have 5 more minutes, we can quickly deal with outliers and then call it a day today.
Please.
Can I take extra 5 minutes?
Sure.
Okay. At least one person said yes. I'm going to go ahead. So what are outliers? Outliers are those points which have an exorbitant amount of influence on the model. That is, if we remove these points, the model will change drastically. That's the definition of outliers. If I remove the point and the model does not change much, then that point is not an outlier. It's not an outlier, right? So how do we measure outliers? How do we determine outliers? We determine outliers using 3 quantities. One quantity called the leverage. Leverage is a quantity we define based only upon the independent variable, X variable. Okay. Then we have another quantity called studentized residual, which is, it uses how much error our model has for a given data point. For that data point, what is the error that you have got? And it's called studentized. Studentized means essentially standardized. Okay. Student T. Okay, that's another historical information. Probably many of you might know. Gossett, when he figured out the T variable, he wanted to publish this finding. Okay. But the company Guinness prohibited him from publishing this result because they thought this is some secret recipe for quality control. Okay, so they prevented Gossett from publishing. So what Gossett did was he published it under the pseudonym student. Okay, so this T is always called student T. The variable T is always called student T. So similarly, what is that essentially? It's nothing but standard score, except that instead of the standard deviation in the denominator, we use the standard error, right? So same way, here is the studentized T. It's essentially standard score, right? And combining both of them, we define a quantity called Cook's D. We define a quantity called Cook's D. And that is what will help us define what is called whether a point is an outlier or not. So for each point, we will calculate leverage, studentized residual, and the Cook's D. And we will check for Cook's D value. There are some guidelines of Cook's D value. Based upon that, we will define whether a point is an outlier or not. Okay. So let me see. Okay, I think it might be a good time to stop here because I think it might go for more than 10 minutes. The way I proceed. So what we'll do is we'll stop here. We'll start with outliers tomorrow. And once we are done with outliers, what we'll do is we'll move on to multiple linear regressions. Okay. So I'll stop here. If you have any questions, please go ahead and ask. Anyway, you have the slides with you. You could go through the slides and come prepared tomorrow. Tomorrow we will start talking about multiple linear regression.
Professor, only one question. In the QQ plot, whatever you've shown, the right plot, So there is some form of representation in this QQ plot, which perhaps indicating that the function which has been assumed to transfer the linear variable, it's not good enough just to get a sense. Okay. Yeah.
So this tells us that the underlying assumption of normality of the errors in the data is failing. Okay. This does not say anything about the relationship between y and x. It's only talking about how the errors in the data are. Okay. Now, what do we do if you find something like this? What do we do again? We have to rectify this, right? So what do we do? No, in Sanskrit there is a old shloka. I think it was written by Shankaracharya. Now it goes like Akashat patitam toyam sagaram pratigachati. Okay, so the statement goes like from the sky, when water drops fall onto the earth, they finally go to the sea. Okay, sagaram pratigachati. They always keep moving towards the sea. Okay? He talks about rain and how it goes towards the sea, and he connects it to theology. Let's not worry about that. Likewise, any of the assumptions fail, we always go back to doing some transformation, data transformation. Okay. So if the normality assumption fails, you go look at the data, see if there is some kind of transformation you can do which would fix. Okay.
So it is not like giving up the regression. We need to do something to bring it this way.
Correct. That's all. Okay. Yes, Sam Young, please go ahead.
Yeah. So if not all the data points in this two plot on the right hand side are equal, so some of these points can change or rewrite our models.
Some of these points?
Yeah. So on the one on the right hand side is pretty bad.
Yeah.
So let's say for our dissertations. So when do we remove outliers, or we have to address outliers?
We do not know whether these are outliers. Okay, we do not know whether these are outliers. Okay? But
should we explain them?
This might be the distribution. Say, for example, instead of the data points falling on this distribution, maybe the data points fall on. Let me do. Where's this? Okay. Instead of falling on a distribution, let me see whether I can draw this. What is this? Freeform. Okay. Instead of the data points falling on a distribution like this, okay, your data points might be something like this. Okay, the left hand side is fairly similar to a normal distribution. The right hand side is what we call a skewed normal distribution. Okay, so the distribution is different. Your residuals, instead of being like this, I have all the residual values plotted on the x-axis and the frequency or the proportion of the probability I plot on the y-axis. So I get a graph like this. If I get a graph like this, then I have normality. If I get a graph like this on the right hand side, this is not normal. This is more like what is called a skewed normal. Okay, so that is what the QQ plot is telling you in this case. In fact, specifically in this case, okay, you see there's a lot of deviation on the lower end, but not too much on the higher end. So this probably is a skewed distribution with some kind of errors also there. Okay, so now technically what statisticians would do is when they find the QQ plot like this, they would definitely look at the distribution, and then from the experience they would know, depending upon if the actual distribution looks like this kind of transformation helps me to bring back to this normality. They would have known by some experience, or there are lots of tables, mathematical tables published. Maybe they will have some information. Okay? So some kind of transformation will then make the data look like a normal distribution, and that's what you have to do.
Right. Thank you.
But Professor, for example, if I have a Poisson distribution, I can never convert it to normal, right?
Oh, that's a. If you no Poisson distribution also becomes close to normal when the number of points. The Poisson distribution is defined by what is Poisson distribution? Poisson distribution is something where you are counting. Okay, so let's say you have a collection of coins, lots of boxes. Each box has some random collection of random number of coins. Okay, and if you plot the distribution, that distribution is called Poisson distribution. And when you have a large number of such collections, okay, your Poisson distribution will also look like a normal distribution.
So now when I have a MLR, I may have few of the variable adapting binomial distribution, few adapting Poisson, few adapting a normal distribution, and so on. And my target variable has a dependency on the mix of these distributions. In that case, I still must do the linear regression. What should I do to transform them?
Remember, we are not worried about the distribution of the independent variables. We are worried about the distribution of the errors in the y variable. This is only the residuals. This is the, remember, we are looking.
Got it.
You remember that we are only looking at the.
Yes.
We are only looking at this.
Yeah.
Okay, it has nothing to do with the distribution of x values.
Okay, so I may have any nonlinear representation, and then I calculate the error, and that error has to be linearly distributed. I mean, it should have a normal distribution, and it should have a homoscedasticity.
Correct. Correct.
Okay.
Okay. Excellent discussion, actually. Okay. This as I mentioned during the first session, I wanted to rush and run, but I'm not able to do because we are having a very, very good, interesting, thought-provoking discussions. Okay, so I'm actually enjoying this. Okay,
thanks.
So as there was a slight mentioning in the last session that perhaps even if we need the extra session,
absolutely,
we have to somehow arrange for it. I want to leave it to you. One of you, please take a volunteer to do this. I am pretty sure that Upgrade and GGU will not agree to extending the course beyond the last date of this course. So I want to know whether any working day, weekday, would be manageable. Okay, I probably will need one extra class, probably. So towards the end of the course, towards the end of this month, some weekday, if all of you can come to a consensus or a majority voting, you please figure that out and let me know. I will manage to get myself free. The time also, I don't care whether it is morning, evening, or midnight for me. Doesn't matter. Okay, time also, if you all can come up with some one extra session during a weekday, we could arrange to cover everything in fairly decent pace. Otherwise, I mean,
will it be before our assignment 2, before the submission of assignment 2?
Yes, before the submission of assignment 2, correct.
Professor, may I have a suggestion to just enable us bring in all these concepts into the assignments? Can we have it a bit earlier, maybe coming Friday or something? Would it be convenient to you?
I'm okay with that. I'm okay with that. Please take a poll in your among your group, in your cohort.
Okay.
Okay. If they are fine with it, I'm fine with it. But let me know a couple of days earlier at least, so that I can arrange with the Upgrade team to arrange for the schedule.
We will internally conduct a poll, Professor, and if we have a buy-in for coming Friday, one of us will take it with Upgrade, and we will let you know, preferably before Wednesday.
Awesome. That will be awesome. Great. Thank you.
Thank you.
Thank you all. Thank you.
Prof, just a quick one. I don't see today's resources in the Upgrade's platform. The slides are not available on the platform.
Really? Which days?
Today's.
Okay. Today's. I see. I'm using this same slide deck from previous session. If you see the dates also from the previous session, because I put everything in one slide deck, and I'm continuing.
Oh, okay.
I have not updated that.
Okay, got it. Thanks.
Professor, you do some additions, corrections during the classes. If possible, please.
I will upload it today after this class. Once we close down, I'll add this to today's sessions. Okay?
Thanks, Professor.
Great. Thank you all. Great talking to you, and see you all tomorrow. Take care.
Thank you.
Thank you.
Thank you. Bye-bye.